Perfect. Okay, so we may start. I don't see ARM people just joined. We're supposed to.
Yeah, I'm here.
Here?
Yep.
Perfect. Okay, so Lucas, right?
Yes, Lucas.
Perfect, Lucas. Okay, so you just first. Okay, we can start our session. I'll just do a brief introduction of the session. And this is like pretty dancey 8 tools session, and we have multiple speakers attending this session, and we almost have no gaps like between talks, so we'll just go fast. So we just have like on the agenda, we have first talk will be ARM Forge tool, and Lucas will be presenting, and we have like Vampir, Vampir talk. Will be just Bill and Bert presenting from Technical University, followed by PAPI utilities. It will be Giuseppe from University of Tennessee, and after that will be Carlo presenting LIKWID. And we finish all of those European contributors. After that, at 4:10, we'll have like American started. HPC Toolkit first goes with DynInst. After that, Canadian TraceCompass and Theia. And at 5 o'clock, we have like advanced AMD debugging support with TotalView for Force. And the last talk will be Tau Performance System, University of Oregon. Now I'm just stopping to share, and please, Lucas, go ahead and share your slide. Okay, we can see it. Please go ahead.
Although we can't hear Lucas.
Yeah. Okay. Can you hear? Okay, Lucas.
Yeah, hold on. For some reason, it wouldn't let me unmute when I was doing the presentation. Sorry about that.
Okay.
All right, can you hear me now and see the slides?
Yes, yes.
Excellent. Okay. So thanks for the ECP committee to have me here. From ARM, I'm going to be talking about Forge and what we've done to provide debugging for the new AMD GPUs, especially what's coming up on Frontier. I'm more of a Forge user. Louise is the primary developer for the AMD GPU additions that we've done recently, and Bo is our sales and customer support specialist for Forge. So I'll do a brief overview of what Forge is for those of you who may or may not have used it, and there might be some things you didn't know were in there. Then I'll go into detail more about the additions for the AMD GPU, including debugging, profiling, and then our performance reports. So what is Forge? Forge is an all-in-one software package. It's designed to have one package that you can install that has both debugging, profiling, and reporting. And I think I'll talk a little bit about the reporting at the end, because to me, that's what distinguishes Forge from some of the other profilers and debuggers out there. It's a great tool that puts it into one page to pass it on. But really, it's a single software package that works on any hardware. It's completely hardware agnostic. And it's going to look and feel the same regardless on what system you're on, which for me as a user standpoint is really great. Before I came to ARM, I was at the DoD, and we had every different technology in HPC available, and ARM Forge was able to work the same on every single piece of technology, which was really nice when I was trying to look at different debugging or performance aspects from different systems. So we'll start the way your product flow would normally work. The first thing you're going to do is debug your code. And DDT is a great graphical interface for debugging code on an HPC. You have everything, from your standard printing variables to stopping on your variable changes, which is really nice. If you think that something is not supposed to change and it does, DDT will stop the program execution and highlight where it stopped and where it is in the source code. If you have any code warnings, it'll give you the error. One that's really great is the read-write on array bounds. Some of us who have been around in software before debuggers were this advanced, we would do our own little padding of arrays and things like that. And so having that there to avoid a seg fault or an illegal memory change is really nice. And then one thing that's really good for applications is detecting your stale memory allocation. So if you don't free your memory properly and you leave it around, and that starts to hog your resources and drag your performance down, DDT can highlight where you're not freeing your memory properly. So this is the slide that we like to show that is probably familiar to most people here, but we'll just go through it briefly. And these are all the different steps along optimization that ARM Forge will help you with. Okay, the first two that we talked about so far are DDT with bugs and analyzing before you optimize. It's really nice. You can see what's there. You get a visual interface with respect to the source code and the stack when a bug shows up. And then the rest is going to be mostly map, which we'll talk about in a minute. You get to see your IO usage, right? IO these days can be pretty costly depending on how much data you have to load and where that data is located. So learning where your IO hotspots are is really important to streamlining your performance. Then, of course, we can detect our issues with any kind of balancing and communication, steps 4 and 5. Map will do that for us. It'll tell us where we're spending time in MPI, how much it's taking, and whether the layout of the processors is ideal or not. We talked a little bit about memory. We talked about not freeing memory in DDT, and map will also have memory statistics available to you to see which subroutines are using memory efficiently or not. We'll see synchronization regardless of what the parallelization scheme is, whether it's MPI or OpenMP, anything like that. You can detect where your synchronization issues might be. And then by understanding how the CPU usage and GPU usage is, you'll see how well your code is vectorized. And then finally, because you can stop and monitor variables in both applications, you'll be able to verify that your program is actually doing what it's supposed to be. So let's talk a little bit about what map is as a profiler and how it can work for you. Like we looked at that roadmap before, we have all the different parts in a nice visual GUI. And what I like about it is the different colors are very easy to determine what's going on in your code. Okay. So for example, you can see here on the MPI imbalance issue, right? we have different colors in the sidebar, and that indicates different usages. So the green is going to be CPU usage, and the bluish purple here is going to be the MPI communication. So you can very quickly visually see where your bottlenecks are, as well as the software will help you guide you to those imbalance points. And you can look at just about everything. Any kind of PAPI event or MPI event or IO event can be monitored in MAP and can be analyzed to see where your bottlenecks are. So it is a sampling-based profiler, so it's relatively lightweight on your application. You can adjust the sampling rate so that if you find that it is sampling too often and interfering with your product execution, you can reduce the sampling rate. Or if some of your subroutines are too fast and missing the sampling rate, you can actually increase it to get those. That's been useful for me because you work on everything, at least I do, from single processor up through thousands of processors. And sometimes on the single processor benchmarks, they can go too fast for some of the sampling rates. So it's nice to be able to adjust that. It does the hotspot analysis for you, much like what you would expect from any profiler. So your top subroutines and functions will be identified, and then you'll get a full stack trace. When you highlight any of the applications, you can get a simple drop down of what's happening, and you can customize this list to tell you whatever you need. You can customize either in the GUI or in the application before you run it, what it'll record for you. The nice thing, like I say, is it's scalable, and it works with just about everything. It works with every parallelization scheme. It works with all the different hardware. It's going to give you this nice colored GUI to tell you what's going on in your code and where you might want to look to investigate your bottlenecks. We've recently added Python profiling. This is really great. I've been using this a lot lately. It works seamlessly with the Python libraries, so I really like it. And it'll work with MPI for Pi as well. And it does mixed language support. So, a lot of us in HPC will write C routines that Python will call, and they work together just fine. And this will allow you to see whether or not you're in your C routine or you're in your Python routine based on the color. So you can visually immediately identify what's going on and where you might want to optimize, whether it's a Python routine or a C library routine, which I think is really neat. It's a lot of Python profilers that are out there today don't do that distinguishing. And so you might not know exactly what's going on and whether it's a Python or a C problem. Another great thing about the Forge system is that you can operate it completely remotely. Like I say, I used to be at the DoD, and it was nice to be able to be just at my home or my office and be able to securely launch jobs on the HPC systems through MAP or DDT. And you don't have to be local. It can be anywhere that you can log into the machine. It supports secure SSH tunneling. So you can launch jobs. You can also analyze things offline. So if you've already run a job and you just want to look at the results, you can just pull those in. We have a couple blogs on our website that talk about offline debugging. You can also load core stacks, all the typical things you would expect from a debugger and a profiler. Now I want to highlight the performance report here, because to me, this is what really helps set Forge apart from some of the other profilers that you might have. And this gives you a one-page summary of what's going on in your code and where the hotspots are and how your code might be improved. Okay, so this is an example of Cloverleaf, which we know is compute bound in this small benchmark. But it'll tell you the percentage of compute, MPI, and IO, or if you add the GPU, which we'll show later, there's a separate section for the GPU. And this is the page that you send to the upper management the people who might be making budget decisions but don't have a lot of time to review the codes directly. You could say, look, my code is 100% compute bound. If you give me twice as much compute, I'll be able to run this twice as fast. So this is something that I found really useful to be able to present to some of the less technical management groups that just need to know why we're justifying these hardware expenditures, why your code is taking as long as it is, and what they can do to help you get it faster. So performance reports is great. It can be run separately from the debug and the profiling. And it's a single launch line, just like both MAP and DDT. And you either get a text output or you can get a HTML output, which has all the nice graphics. And so, like I say, to me, this is a really great tool for a single page summary of what's going on in your code. It doesn't take a high level of technical knowledge to understand. So now what I'll do is we'll talk about the features that were added for the AMD GPUs. The great thing about what the developers did was they tried to really make ARM Forge as agnostic as possible. So if you've used ARM Forge with CUDA before on NVIDIA GPUs, the AMD GPU debugging is going to look very, very similar. What they've essentially done is taken anything that was labeled CUDA and just turned it into GPU. So it's going to look the same, it's going to feel the same, it's going to act the same. So when you launch DDT with an AMD GPU job, you can debug both the CPU and the GPU at the same time. We have support for the latest 5.1, and the goal of the developers is to remain in sync with whatever gets released on Frontier. So as Frontier increases their AMD ROCm API versions, the development team will be releasing hotfixes to maintain that concurrency. So we're always going to have the latest version. We work closely with AMD to make sure that we've got the version of their API ahead of time if we can get it, so that we can be working ahead of the schedule and we won't be lagging behind. This is covered by existing GPU licenses. So if you're not familiar with Forge and their licensing, the way it works is you can buy different packages. And if you get the GPU package, which used to just be CUDA, now the AMD ROCm is covered in that. When you build and launch your software, it's relatively easy, right? We're trying to make this as simple as possible to use. So if you use the -G option, right, that gives us the debug symbols, allows us to relay everything back to source code. Just like any other launch with DDT, you just use the DDT command line and the program name. The --ROCm tells us to look for the ROCm libraries. If the ROCm libraries are in your environment and the program calls the ROCm libraries, you'll immediately get the GPU options in your DDT setup. You can also launch it graphically from our run dialog in the client. So if you're at home and you're on your laptop, you can just fire up the Forge client and launch that ROCm application just like you would any other type of application. You can run ROCm and MPI together, but an OpenMP, but you can't run ROCm and CUDA. So what do we do? What kind of features do we have supported? Like I say, pretty much everything that you can do with CUDA, right? So you have complete control over your GPU threads. You can play, pause, you can set breakpoints, you can set trace points, you can set watch points, you can monitor variables, you can step. I think the biggest difference is that you have to kind of step all threads together, and that's a limitation of the AMD API that comes with their debug library. Inactive threads we can't monitor, so we just monitor all the threads in a wavefront at once. So you can run through the line, you can see your stacks in your register. You have assembly view available for anything running on the CPU. And the nice thing, like I say, is that if those libraries for HIP are in the path and it detects a call to those libraries, you're going to automatically detect the ROCm libraries and bring up the supported features. So for those of you who may not have used Forge before, with a GPU, it's relatively simple. There's a section in the GUI that allows you to select the block and the thread. And then you can see everything that you want about that block and thread, right? It'll tell you the number of lanes in the wavefront. You can look at all the variables that are there. You can look at what current line it's on, and it'll relay you back to the source code, and you can evaluate variables that are on that line. You also can use it in the what they call the parallel stack view, and this is a quick view if you have a lot of different kernels running at once. This one has a simple matrix example, so it's only got one kernel running. But if you have multiple kernels running at once, you see a breakdown of everything that's running, and you can select them from this stack view, and it'll give you the more detailed view. This is a nice visual progress bar that allows you to see where you are in your kernel, in your source code, and what's active and what's not active. The varying degrees of color indicate the activity and the relative size of the threads or wavefront that's available to you. And anything that's white is either waiting or is not scheduled to run. So you can see what's idle just from a quick glance at the progress view. This is just being able to see what devices are attached but hopefully you know that when you allocate your sources and run your job. Let's talk a little bit about profiling. I'm trying to skip through everything really quickly. So when you move to map and you start profiling, you get a nice visual breakdown again of the GPU versus CPU. So if you look at the main thread activity, right, we have different colors to indicate exactly what's happening in the thread. The green would be CPU activity and the purple would be the GPU application. So you can see initially we kind of fire everything up, and the CPU does some work and passes off to the GPU, and the GPU and the CPU are working together. The GPU utilization starts at 0, which is expected. And then once it gets its instructions and the kernel fires off, we've got the GPU here on this example working at near 100% for most of the execution time before it passes back to the CPU. So really quick, easy overview of what's going on in your kernel. And then down here, you've got your stack view again that gives you a breakdown in percentages of functions and source code as to where exactly you're spending most of your time. And the color code again will tell you whether it's the purple for the GPU or the green for the CPU. So you can very quickly see what's happening in your program, where your hotspot might be, and what's happening either on the GPU or the CPU. And this this set of metrics is configurable. We'll go through that in a second. And just like with DDT, we have the custom launcher. You can launch it graphically through the run dialog, or you can launch it in a script through the command.
How are you?
This morning.
Oh, no, that's fine.
So here's a close-up of the GPU metrics. And we have everything all the way down to power consumption as to what's happening at the GPU level. This is with the professional license. So if you don't have the professional license, you might not get the power consumption, but you should get with the GPU license, the utilization and memory and all that sort of stuff. We have preset menus of what most of our customers like to look at in groups, but each individual metric can also be individually selected or deselected. So if you go through the menu options, you'll be able to see what you want to see and not have to look at anything that's distracting. This is again the kernel tab that indicates what's active and how often it's being used and whether it's CPU or GPU. If you click on any of these stack views, it jumps you to that source code. And then, like I said, we have the performance reports for GPUs. It's the same as if you would run on just the CPU. and it adds this box that talks about how the GPUs were utilized, how much memory was used, and the peak and mean utilization. Again, this is a nice little one-page block that lets you know whether or not you're using your GPU effectively and what might be able to be quickly modified to use your accelerators a little bit more efficiently. So I just want to quickly note what's been going on in the development process. We're expecting a general release for the ROCm AMD GPU support in the latter half of 2022. The idea is to go live with Frontier. So we're, again, keeping pace with them and making sure that our libraries will work as Frontier gets deployed. We've been testing on the Crusher system and in our in-house system to make sure that as many bugs as possible have been ironed out. Just to quickly go over what might not work initially. So right now, and this is an AMD API issue, you can't see the inactive lanes. So if your thread on a GPU is currently inactive, which would be white, and you try to click on it, you're going to get a warning box that says, hey, we can't show you this right now, and you're going to get sent back to your last active thread. For map, we don't have OpenMP kernels on the AMD GPUs yet, but we'll get there. And this for the ROC libraries, right now, if you were to get a preview version, the debug symbols in Forge are based on 4.5 rather than 5.1. So what happens is it loads those debug symbols in the background, and there might be a small issue, but we haven't seen it really cause any problems. And then once we go live, all the debug symbols will be reincorporated from the correct library. And if you have any questions, please go to our website. You can click on that. That'll give you a contact form. You can also reach out to whoever your Forge contact is for your location and your license, and they'll get you in touch with the right people. And I think I'm out of time and just got through it.
Thank you, Lucas. So you have one question on the chat, like, can Forge DDD debug OpenMP offload code now? You just may respond to this like in the chat, and we just follow up with other speakers. Thank you very much. You may unshare.
All right, thank you.
Slides. And second speaker will go. Thank you, Bill. Bill, yeah, okay, perfect. We can see your slides. We cannot hear your voice.
That's because I hadn't unmuted and I hadn't said anything yet.
Okay, now we can hear you and we can see
Excellent.
the slides.
Good.
Please go ahead, Bill.
So, I'm going to be talking about a couple of the tools we work on at TU Dresden, SCORP and Vampir, and what we've been doing to add support for ROCm and for AMD GPUs in general to this. So first, a brief overview to make sure that everyone is familiar. So we have SCORP, which is our measurement system, and Vampir, which is our visualization tool. And for each of these, I want to give a bit of background, how they're used in general, and then specifics of things we are doing to make life with AMD GPUs better. So without further ado, let's start with background on SCORP. SCORP is a system for, as I said, instrumentation and performance measurement. And this can be used to produce a couple of different types of results. We can either build a call path profile with Cube4 data format, or do tracing with the OTF2 format, which we'll be focusing on tonight. And we support a wide variety of parallel paradigms, multi-process, thread parallel, and accelerator-based. This is an open source measurement system. It is portable and scalable to all major HPC systems. Our initial funding was through BMBF and the DOE Prima project. And we're now over 10 years into the project, and funding continues through a variety of sources. How SCORE-P works. We have at the very bottom our application, and sitting above it, we have these things that we call adapters that intercept and instrument these various parallel paradigms, instrument source code, collect some sampling data, and that feeds into our measurement system, which can also integrate hardware counters or other so-called metric values. This infrastructure then produces our profiles or traces, which are consumed by a wide variety of tools. If I wave my hands vigorously, it sounds almost as simple as the slide is. Usage, which is what you guys actually care about. The executable for SCORE-P is a smart compile and link step wrapper. By this, I mean we try to look at the existing compile line or link line and figure out, based on that, what adapters we need and what the right thing to do for instrumentation is. And this can be manually steered via flags that are passed to this executable. And when you're working with simple make files, this works great. Modern build systems, however, do require modern solutions. So we also have these wrapper scripts that are SCORE-P name of a compiler. And these are suitable for passing via your standard compiler specification to auto tools, to CMake, whatever. And the point of these scripts is that you can control what instrumentation gets enabled when, based on environment variables. So, the simple and obvious case here is that when you're configuring your application, your configure checks will most likely fail if you try to build them with instrumentation. So your configure step you would run with the wrapper disabled and no instrumentation happening, and then build time, you actually instrument things. And what this means is that if you have a HIP build of SCORE-P, SCORE-P HIP-CC is fully equivalent to SCORE-P HIP-CC. We have a wrapper that just works most of the time. So a standard example we like to give here is this BTMZ benchmark from the NAS parallel benchmark suite. And here it's very easy to modify the make file so that it will read a prep environment variable. And we simply put prep equals SCORE-P in, and here we have a prep in the make file that expands to SCORE-P, and you get instrumented code out. Now, of course, you also need to be able to configure the measurement system a bit at runtime. And here, one of the key things to know about is the SCORP info command. This will give a full list of the environment variables that SCORP will listen to. And of course, for a build that supports ROCm instrumentation, there will be a few new ones, which we will see in a couple of slides. Okay. If we're going to have SCORP work on ROCm, as many of you guys know, SCORP needs to be built for a particular tool chain so that we build the right set of adapters for the code that you're trying to build. So the configuration inputs that you're going to want will respect ROCm path in your environment. Enable HIP will force our configure to look for all of the various ROCm libraries. And of course, we have a relatively standard set of with arguments. Most of the time, with a sane setup, you shouldn't need these. But in the event that you do, there they are. Also, most of the time, our auto tools should detect that HIPCC on the back end is a Clang-based compiler, and we should instrument accordingly. If that turns out not to be the case on a given system, a given module configuration, you can specify what the backend compiler suite is supposed to be like. We do recommend ProGenv AMD on systems like Crusher rather than ProGenv Cray right now. But they both should work, and we are working on making that as robust as we can. Usage. So, as I mentioned, we're going to have some new flags, and we're going to have some new environment variables. The flags that we care about are just SCORP --HIP, or adding this to SCORP wrapper instrumenter flags if you're using a compiler wrapper. And that is all you need to get the ROCm adapter in place for your binary. And then you set the SCORP HIP enable variable to a comma separated list of various types of instrumentation that we can perform. So, yeah, you can choose to instrument or not instrument kernels, transfers, allocation, synchronization, and to enable or disable ROCtx user instrumentation. All of this should be very familiar to those of you who've used SCORP with CUDA. We used that as our model for how should this work so that users are not astonished. It is our hope that there are no surprises in this interface. So I do have to look into our infrastructure briefly here. So OTF2 has a notion of locations and location groups, which is how it structures event streams in the trace. And before we started working on ROCm support, we had the model that all locations, which is to say either threads or streams, are members of a single location group per process. And that obviously doesn't map very well to modern systems with multiple GPUs and so on. And now we have this restructuring in place. This was released at the end of 2021 in OTF2, and we're working on getting that into our measurement system now that allows location groups to be nested. Now, why does this matter? So there's a bunch of things that this makes easier for us technically, but the big thing from a user point of view is that each location group has a homogeneous, consistent set of metrics for all of its locations. And obviously that doesn't work very well if you're trying to have metrics on the CPU threads and GPU streams. And this structure lets us specify metrics separately for CPU and GPU. This is actually going to be a key feature to enabling us, hopefully, to use PAPI as a metric source for both CPU and GPU events simultaneously. We've been working with those guys regularly on how should this look and what do we need to do to let us take advantage of all of the cool stuff they've done. And we will see in the Vampir section what this new location structure looks like. So on that note, let's switch over to an overview of Vampir. So Vampir is a trace visualizer. And what we want to do is show you the dynamic behavior of complex parallel processes. We collect data with score P as a trace, and then we visualize it in Vampir. And you can see this screenshot on the right with a bunch of our standard useful views of the application. And Vampir is good for answering some of the more detailed performance engineering questions that are out there, like what actually happened in execution at a particular time on a particular processor thread. What do my communication patterns look like? Are there imbalances? How do they affect parallel execution? Do these imbalances change over time? So it's important when we're talking about trace visualization, understand what it is and what it isn't. This is an alternative and a supplement to automatic analysis tools like MAP, like Scholastica, that will try to give you a automatic diagnosis of your problem. We will show you what the application did at any level of detail that was recorded, and we will give statistics and performance metrics. We will do this through two basic types of interfaces. Timeline charts that have some time axis that you can zoom and scroll on, and then we'll show what the application was doing both in computation and communication during that window. There's the master timeline and process timeline that are important charts there, which we can see in these top two windows on the left. And then we have summary charts that will provide quantitative results, profile-like results for the currently selected time interval. So here we see the communication summary window, the function summary, and these are respectively a data transfer profile and a CPU time profile of whatever window is selected in the timelines. So how does this work with accelerators? Well, first let's talk about the new features. We've added devices and contexts. So previously, if we were looking at the timeline, these two lines for device and context would be missing, and we would just see one line per stream. Additionally, accelerators in Vampir are now fully vendor agnostic. So all of the CUDA versus PIP versus one API versus whatever new hotness develops 5 years from now, that's handled by Scorpy. We write meaningful names into the trace records, and Vampir simply reads those. Accelerators are accelerators. Okay. As for how we would do performance analysis on a GPU application, so we've got here a trace from the LSMS material science code. I did try to get this running and instrumented on Frusher today. Did not get results in time to show you guys tonight. But we do have a slide with CUDA results, which should at least explain the principles. So you can see here, this is the old style of trace recording with master threads and simply a row per CUDA stream. And even this will let us take a deep dive on what sort of communication is happening between hosts and devices. So here in the master timeline, we will see different color rectangular blocks for what is on top of the call stack at any given point. We see, based on the function summary, what's executing on the GPU is most likely this Fermi GMM kernel for most of the time. And we will see these diagonal lines corresponding to memory transfers. Great, but what does all of this mean? We have the details, but we need to interpret them. And where we start here is with the communication matrix. So we've zoomed back out here to look at the entire application and not just a single window. Our communications have been consolidated into these circles representing bursts. And we have the communication matrix itself. that tells us how many messages went from various senders to various receivers. And we see here that this first stream is behaving very differently from the other two. So we
Bill,
have
you
two
have
streams.
1 minute.
Sorry, I will be quick. But we have this imbalance that we might want to look at. We also have the shared resource timeline, which lets us get a device-based view of kernel executions. This is the best tool for analyzing multi-GPU scenarios and getting some insight as to how the hardware is actually being used. So here we see that these streams get unified into the timeline of device 0. And the quick summary. If you already know how to use Scorpion and Vampir for any accelerator, you know how to use them for all accelerators. We're going to have both AMD GPU support and host OMPT support officially released in Scorpion 8, coming hopefully later this year. We have started on OMPT targets development. We are working with the tools working group there to make sure that we actually can work with real runtimes. Here's a link for where to get development tarballs if you want to get a jump on things. And we will, of course, take bug reports, questions, and feedback at our usual support emails. Thank you much. I will hang out briefly to answer questions in the chat or just send email. Thanks.
Thank you, Bill. Please send questions on the chat and will be responded. Okay. Giuseppe, can you hear me?
Yes, I can hear you.
Go
can
ahead,
you hear
try
me?
to share your slides.
Okay.
Okay, we can see.
All right. All right, hello everyone. So today I want to give an update on the new features that will be in the next release of PAPI concerning AMD GPU support. I guess people in this audience are already familiar with PAPI to some extent, but for those that are not, I would like to spend a few words on what PAPI is and what it can do for its users. So chip makers have been putting specialized register to count hardware events on their devices for decades now. And each of the vendors has its own interfaces and naming scheme for those counters and corresponding events. This might even change across models from the same vendors. So it becomes really hard for software developers and domain scientists to access those counters directly because of their heterogeneity and lack of standardization of the interfaces. So what PAPI does is to address this problem by providing a uniform interface for accessing hardware performance counters across a wide range of devices and vendors. And through PAPI, the users can see the relation between the performance of the software and the hardware events happening on the devices and use this information to make improvements to their codes. So PAPI is a long-running project with more than 20 years of longevity. When the project was started back in 1999, PAPI only supported CPU hardware counters, as these were the only one available at that time. Today, PAPI supports CPUs from different hardware vendors and ranging from AMD, ARM, IBM, and Intel. With the introduction of accelerators as complementary compute devices in 2009, PAPI was completely redesigned and moved from a monolithic CPU-only library to a modular multi-device library. So such modules in PAPI are called components, and each hardware device might have one or more of them to support different aspects of the hardware. This modular design also allowed for non-compute devices to be integrated within PAPI, things like network cards, file system, power management, and even virtualization frameworks such as VMware and KVM that are very popular in clouds and data centers. Starting from 2018, PAPI also supports software-defined events through the SD component. This component basically allows users to monitor not only the events happening in the hardware, but also events that are exposed by different libraries in the software stack. And this library uses a companion library called the libsd to define and expose those events to PAPI users. So in terms of AMD GPU support, PAPI enables performance monitoring on ROCm-enabled devices through the ROCm component. Hardware counters are accessed by the component through the ROC Profiler library provided by AMD. And we now have a newly rewritten ROCm component that will be in the next release of PAPI that supports full ROC Profiler counter semantics. The same was not true for the old component, the one in the previous release of PAPI. And we will see in the next two slides what this semantics entails for the users. Finally, the new ROCm component also supports multi-threaded monitoring and counter sampling, both not supported by the old component. So ROC Profiler distinguishes two modes for accessing hardware counters in ROCm devices. One is called the sampling mode, and the other one is called the intercept mode. The two modes differ in the relation expressed between the value of the counters and the work done by the hardware. In sampling mode, for example, the value of the counters is a reflection of what is going on in the hardware at a certain moment. What this means is that whatever kernel is running on the GPU when the counters are read affects their value. So the GPU can be running any arbitrary number of kernels concurrently, and this might even belong to separate applications. So here on the left of the picture of the slide, there is a GPU that is running multiple kernels concurrently, and these all affect the value of the counters. In intercept mode, on the other hand, on the right-hand side of the slide, the value of the counter is a reflection of only one kernel running on the hardware at any given time. And the way that the GPU runtime achieves this single kernel running on the GPU is by enforcing serialization on the GPU itself. So these are basically the main differences between the two modes in terms of kernel granularity. Sampling and intercept mode also have different time granularity or read granularity. In sampling mode, kernels can begin and end at different points in time, potentially overlapping. So here on the left, we see the 4 kernels that we had in the previous slides. These begin and end at different points in time. They can also overlap, like in this case. And what the user can do in terms of measuring or counting events is the user can start and stop counting events at any point in time in this clock. So the time granularity is user-defined, is arbitrary. In intercept mode, on the other hand, on the right-hand side, only one kernel can run at any given time, and counters cannot be started and stopped anywhere, but only at the boundaries of the kernel. So they can be started at the beginning of the kernel and stopped at the end of the kernel. They cannot be started and stopped here in this gray region over here. So to summarize this slide, basically the takeaway is that in sampling mode here on the left, the user can slice time wherever he wants, and the value of the counters will be a reflection of whatever kernel is intercepted by this slide. In this case, for example, we have 3 kernels that are intercepted, the red, green, and purple, and the counters will be affected by these kernels running on the GPU at that time, but they will not be affected by the light blue kernel that is left outside of that region. Okay, so the new ROCm component support both sampling and intercept mode that we have just seen, whereas the old one only supported, the old ROCm component only supported sampling mode. In the new ROCm component, the mode can be selected by the PAPI users through this ROCPHSA intercept environment variable. By default, when the variable is unset or set to 0, PAPI selects sampling mode. If the value of the variable is set to either 1 or 2, on the other hand, PAPI selects intercept mode instead. What is important to know for the user is that both modes are exposed through the same PAPI interface, so they work exactly the same. Thus, counters are read in the same way for the 2 modes. However, the 2 modes have different semantics, and the user has to keep this in mind when interpreting the value of the counters. The old ROCm component also only supported single thread monitoring. In PAPI, this means that only the thread that calls PAPI library init is allowed to create event sets and monitor hardware counters through them. However, application can be multi-threaded, and each thread might be responsible for a different task that is executed on a dedicated GPU device. Therefore, it is important for application writers to be able to monitor those tasks independently. Yeah, is there a question? Okay. So in multi-thread monitoring, on the other hand, each thread can create an event set and use it to monitor an associated devices or group of devices. Once again, PAPI users have to keep in mind the semantics of they use the profiling mode. In sampling mode, for example, recalling the sampling mode, it does not make sense to have 2 threads monitoring the same device because counters are global, and the 2 threads calling PAPI start at different points in time will affect each other's readings. In order to let the users know what is allowed and what is not, PAPI returns error codes every time 2 separate threads try to add events from the same device to their event sets while using sampling mode. So we warmly encourage our users to always check the return values to make sure that PAPI supports the expected functionality. In intercept mode, on the other hand, it is perfectly fine to have 2 threads monitor the same device because the kernels will never run at the same time and will be serialized. So there is no conflict in this case. This is just a simple example code of how to use the sampling mode. Basically, in this slide, we are setting the ROCPHSA intercept equals 0 to select sampling mode within the code, but this can be done, of course, outside the code. Then there is a call to PAPI library init in order to initialize the ROC profiler library. And this PAPI thread init call is to basically let PAPI know that the user will be doing monitoring from different threads in the application. Then there is this OpenMP parallel region that spawns 3 threads. And each of these threads can basically select a dedicated device, create an event set, add events to the event set, and start monitoring some work that is launched on the GPU, and then stop the counters, collect the values, and potentially print them. Intercept mode is exactly the same code. The only difference is that ROCm intercept environment variable is set to 1 instead of 0. And in this case, each of the threads over here is allowed to monitor all the GPUs, whereas in the previous case, each of the thread was only allowed to monitor the corresponding GPU to avoid conflicts. All right, so far I've shown you some of the examples using the low-level API. However, the low-level API is predominantly for expert users and tool writers. PAPI also has an high-level API that sacrifices some of the flexibility of the low-level API for additional simplicity, and as such is intended for more inexperienced users or users that approach PAPI and want to do some simple monitoring of their application with it. So one of the flexibilities that the high-level API sacrifices for simplicity is the ability of managing different events across different threads. By doing things like this, the high-level API can reduce the 8+ interfaces in the low-level API to about just 4 interfaces. Events in the high-level API are defined using an environment variable called PAPI events, and all the threads in the application get the same events defined by this variable. So what PAPI does is it looks at the PAPI events environment variable, it checks all the events in it and associates all those events to the corresponding components that monitor the corresponding hardware device. And all the threads basically get the same events. There is no per thread events that can be specified using this PAPI events interface. So this is the limitation, the sacrificed flexibility. What this means in terms of profiling modes, because the user also needs to keep in mind what profiling mode it is currently using, is that in sampling mode, it is not possible to use the high-level API in multi-thread monitoring because of the previous considerations, and these are that two threads are not allowed to monitor the same device at the same time because they will interfere with each other's readings. Intercept mode, however, works without any issue with the multi-thread monitoring the level API for the same consideration as before, because threads will run kernels on the hardware at different non-overlapping points in time. All right, this is an example of what can be done with the high-level API. In this specific example, we have the report generated by the high-level API for 2 events, sets A and B on the corresponding threads. Each thread uses only one device, but has events for both of the devices. Because as said before, PAPI events environment variable applies to all the threads. So all the threads get the same events, but in this case, because the event set A is, red thread is basically running only on GPU device number 0, only the counters of this device will be measured, whereas the device 1 reports 0 counter. And the opposite is true for thread number 1. Another feature that is enabled by the new ROCm component is counter sampling. So this feature is especially useful for high-level tools that do sampling, like, for example, HPCToolkit. I don't know if they, this is a feature that was not present in the previous version of the ROCm component. It is only present in the new version of the component. So what counter sampling allows to do to the user is that the user can call this PAPI overflow function to register an event from the event set. And this event will be overflown using a threshold defined also by the user. And also the PAPI overflow also take a user callback to call when the event overflows. The problem is that a ROC profiler itself does not support overflow in hardware. So PAPI has to emulate overflow in software using high precision timers. When PAPI register timers that expire, let's say, every 100 microseconds, PAPI reads the overflow counter. It checks the value of the counter against the threshold. And if the counter overflows, PAPI calls the user callbacks. Once again, users have to keep in mind the semantics being used, the profiling semantics. For example, it does not make sense to use a counter sampling in intercept mode because the read granularity in this case is fixed. Only the timers can only be started and stopped at the kernel boundaries, not in between. So it doesn't make sense to use intercept mode in counter sampling. Only sampling mode from ROC profiler makes sense in this case, and PAPI disable counter sampling in intercept mode to prevent users from doing things that don't make sense. So the new ROCm component is not yet in master. It will be merged soon, hopefully next month, and this will be along with the release of the new version of the library. So at the moment, the component is sitting in a separate fork that can be cloned from the reported link over here. And once the fork is cloned, it is possible to configure PAPI with ROCm support by exporting the PAPI ROCm root environment variable to the ROCm installation directory. And after that, it is possible to check out the branch for the new component, which is called ROCm rewrite, and configure the component and build a library. The component comes with an exhaustive set of tests that can be consulted to understand how the component interacts with the PAPI public API. The tests are divided mainly into 4 categories. There is a single thread monitoring set of tests that basically have only one thread doing the monitoring for all the GPUs using only one event set. There is also a set of multi-thread monitoring tests in which each GPU is handled by a separate thread that does its monitoring independently. There is a set of single kernel monitoring tests in which one thread monitors one kernel launch on a single GPU one at a time. So there is basically a PAPI start, launch kernel, synchronize, PAPI stop, read the counters. And also a multi-kernel monitoring test, a set of tests in which one thread monitors multiple kernel launches on a single GPU. So instead of doing a single kernel launch and then instrument this kernel launch with PAPI start and PAPI stop, multiple kernels are launched in a for loop, and PAPI monitors basically all the threads, all the kernels running at the same time on the GPU hardware. I also want to spend a few words on how to configure the ROCm component properly to make it work as expected. In order for the component to work correctly, the user should call PAPI library init before any IP and ROCm interface. So what PAPI library init does is to set up the ROC profiler environment, which is comprised of these 3 environment variables. HSA tools lib tells basically HSA init the runtime system in ROCm. To load libroc profiler has a plugin tool. ROCp metrics tells libroc profiler plugin tool where to find the definition of the metrics for the GPU hardware. So this is an XML file typically. And ROCp HSA intercept is the environment variable that can be used, is under the user control and can be used to set the profiling mode in order to select the appropriate or the desired counter semantics. The users are also free to set any of these variables themselves, and PAPI won't override them. One possible usage of this behavior is that, for example, the user has some development set of metrics that is separated from the main installation of ROCm and ROC profiler, and it can point basically to this development or experimental set of metrics by setting manually these ROCp metrics.
Giuseppe, you have time?
How much time I have?
1 minute. 1 minute
okay.
to finish.
All right, I'm done. So if the user cannot call PAPI library init before any HIP or ROCm call, users can still make the component function correctly by doing the following. So they have to explicitly export HSA tools lib to the libroc profiler 64.so, and also export this ROCp tool lib environment variable to libpapi. And what this ROCp tool lib does is to basically offload the initial initialization of the ROC profiler environment to HSA init, so the HSA runtime. Some tests that use this type of initialization are reported here. These are high-level interface, high-level API tests that can be checked for understanding how this works exactly. So I encourage attendees to do that. So PAPI is also a very successful project, and part of that success stems from its adoption by other successful projects, both within the ECP project and outside. So this is a hopefully comprehensive list of tools and other projects that use PAPI to access hardware performance counters. So this is my last slide. I would like to remark that we have this new ROCm component that should be improving a lot on the old one, and we need feedback from the users. So please go check out the code, play with it, and let us know if you find any issue so that we can fix them before the release.
Thank you, Giuseppe.
Thank you.
Okay, so you may stop sharing, and Carla, please go ahead and share.
All right, I'll start my sharing. I hope that you can hear me.
Yeah, we can hear you. We don't see any slides at the moment. Okay, we can see your slides.
Great.
Okay, please go ahead, Carla.
Just let me quickly rearrange my screen, since currently it's being displayed on the wrong screen. All right, we'll go this way.
Yeah, looks better.
All right, cool. So good afternoon to everybody. Today I'm going to give you an introduction of Liquid with GPUs, and a couple of words from my side. So my name is Carlo, and I'm part-time part of HPE as a technology consultant. And on the other hand, I'm a PhD student who's part of Martin Schulz's chair of computer architecture and parallel systems. And in the last couple of months, we've been closely collaborating with Marcel and Thomas in order to get Liquid extended by the GPU component. And for today's talk, I've basically prepared a small agenda. First of all, I like to give you an overview of Liquid. In general, what is Liquid, and then take a brief overview on the code architecture. The second part is getting Liquid with GPU support in order to get things running, your system prepared to use Liquid. Then we will take a look at how to use Liquid, and for today's session, I will focus on the Liquid Marker API. And then we'll have a close look on the roadmap, and then I will, of course, conclude this presentation. All right, let's get into this presentation. First of all, what does Liquid stand for? Liquid is an acronym for Like I Knew What I'm Doing, and it's basically a tool developed by the HPC group of the RRZE at the Friedrich-Alexander University in Erlangen-Nürnberg, in short, V. And Liquid is a tool to get aggregated hardware performance and more recently energy counters from various components and architectures of the system. And today we've supported CPUs, different architectures, as well as GPUs. And in the last couple of months, we've been focusing on extending Liquid by the following capabilities. First of all, extending NVIDIA GPUs with an energy backend, and then more importantly, introducing AMD GPUs in general, and more specifically with regards to energy as well as performance counters and their respective backends. All right, so let's take a brief look on Liquid and its code architecture. So Liquid has a northbound API, or more commonly said, CLI commands and tools. And the most important ones, which I'll also cover later on in this presentation, are Liquid topology and Liquid perf counter, Liquid pin and Liquid bench, amongst others. And Liquid topology is a tool providing system topology information, and is, in our case, more often used to just get information of the current system and its capabilities. The second one is Liquid perf counter, and Liquid perf counter is a tool which enables us to measure various hardware performance and energy events. And it lets us monitor specific counters as well as aggregated groups, which make analysis more easier for us when analyzing our results. Then we have Liquid bench, which is a set of micro benchmarking microkernels applications, which enable us to run an application quite quickly in our target system. And then we have Liquid power meter, which enables us to use REPL counters. Then we have a couple of other applications which I'm not going to cover throughout this presentation, but you can look them up either in this slide deck or later on in the documentation. All right, then this set of CLI commands and utilities is in general calling a mid layer of source code. And in general, we have typically an entry point for the marker API, which enables us to specify regions within our source code, and I'll cover this later in detail, as well as an Lua interface to basically make calls towards this mid-end without modification of our application. These entry points have a connection to the respective backends. On the one hand, we have a counter backend, which is mainly responsible for querying events in their respective performance group, or if they're standalone, of course, standalone events. And topology information is queried by the respective topology backend. And on the right-hand side, we have several integration tests, which are orthogonal to this mid-layer and are mainly used for development as well as measurement purposes. Then at the very bottom, we have, especially in the GPU context, several third-party libraries, which are not part of LIKWID by itself. And these are typically system libraries and firmware components, which are then queried by LIKWID. And as I've already said, we've spent a couple of weeks in order to extend LIKWID by the respective AMD GPUs. And in order to get the support into LIKWID, we first focused on extending LIKWID topology to get the system information out of our system. Then we started to modify LIKWID perf counter to really measure applications without having to modify them. And then we have initial micro benchmarks in place, more specifically the stream benchmark, which I'm going to show you later on, to get initial measurements to verify our implementation. And of course, LIKWID power meter, which is then responsible for doing power related modifications on our system. In the middle layer, we've implemented the corresponding marker API mid-end with the respective ROCm marker API, as well as the AMD/ROCmon related Lua interface. And both of these entry points have their respective counter/topology backend. And we have also several performance groups in place. And at the bottom, we're basically using HSA as well as the well-known ROCm HIP, ROC Profiler, and ROCm SMI libraries. All right, so what do we have to do in order to get things running? The overall process consists of 3 steps: download, configure, and compile and install. So downloading LIKWID is pretty straightforward. Do a git clone, and please note that at the moment I'm pointing to my own GitHub repository, but in the near future, and we're talking of 1 or 2 weeks, I will merge my changes into the main repository. So please go into the main repository and get the AMD supported version of LIKWID out of there. And then of course, we're going into the LIKWID directory, which is the second command shown in this slide. After going into our LIKWID directory, we will see the main configuration file, config.mk. And in order to get LIKWID running with AMD GPU support, you will have to modify a couple of variables within this file. First of all, we will have to set whether we want to use the ROCm support or not. And if you set the ROCm interface variable to true, shown here, LIKWID will compile with ROCm support. Then you have the possibility to basically modify other system or the path to the system libraries. HSA include, ROC Profiler include, HIP include, RSMI include variables in case you have a non-standard installation of the related corresponding ROCm tool. If you have a standard installation of ROCm in place, the standard values should already be sufficiently set so that you don't have to change anything besides the ROCm interface variable. A quick heads up, at the moment we're having one known issue which is occurring during compile time, actually linker time. We're seeing at the moment multiple definition of the printed variable. And this is a known issue, and we've already opened up a GitHub issue, and the workaround that we're currently using and which works quite good is to simply change the definition of this variable from constant unsigned to static constant unsigned in the respective header file. Having this change in place, you will not encounter the linker issue any longer, and you will be able to use LIKWID. All right, after we've configured our config.mk file, you will of course then have to make install. Please note that sudo is not required for most of the features of LIKWID. In case you should use sudo, you're most probably already aware of the fact that you should sudo, and it's definitely not required for GPU related measurements. All right, after we've built LIKWID and installed it in our target directory, we're then checking whether the installation is working. And in order to do so, we're changing into the installation directory shown here. And then out of curiosity, we're using LIKWID topology to see whether there's an output with regards to GPUs or not. If you're seeing GPU related output as shown here, chances are pretty high that the compilation of LIKWID succeeded, and if not, something went wrong. Okay, now that we have a running setup of LIKWID, we're then able to use the LIKWID marker API. And the LIKWID marker API is pretty handy if you want to use several specific events without having to modify the application later on. And for this tutorial, I want to give you an overview to see the whole process from implementing an application, then compiling the application, and then basically gathering and analyzing the corresponding output of LIKWID. And I want to measure the power average consumption. I want to measure the memory usage. I want to see how many scalar ALU instructions have been issued, and I want to see how many number of waves have been sent to the SQs. And this is just an arbitrary set of events that I've chosen, first of all, due to my background with regards to energy efficiency, as well as with regards to the computing capabilities. And the system under test is basically a system with two MI100 GPUs, but for sake of this tutorial, we've only used one of these two AMD Radeon Instinct GPUs. All right. Let's go into the marker API. So first of all, the marker API is pretty handy if we have an application where we want to provide a more fine-grained insight into specific regions within the code. So we're on the one hand able to define regions within our source code, and then on the other hand, we're able to measure performance and energy counters for each region. And what is pretty handy, that we can define our performance and energy counters outside of the source code of the application by making use of environmental variables. So we do not have to change our application and compile it every time we're trying to get additional events or other combinations of events, but we can simply change the environmental variable. And in general, as I've already said, this enables us to get a fine granular insight into the code and its performance with varying energy and performance counters without having to recompile the application. And the steps for utilizing Liquid's marker API, first of all, we have to modify the source code. More specifically, we will have to define the region, set them up properly, and so on. Then we'll have to compile the application. We will have to execute the application, and then we will have an evaluation of the results. And let's take a quick look of the modifications that need to be performed. First of all, we have to include the Liquid marker headers, which of course hold all of our definitions for the macros, functions that we're calling, and so on. And then we have our application. And the first step is to initialize the marker API with respect to the ROCm library. Then we have to register each region that we're going to use. In this case, I've chosen one region with the name region name for sake of easiness, but you can of course have arbitrary many marker regions in place. Then the next step, after we've registered our region, we can then start our region, launch our kernel, and then stop our region, and then close the region. And now I'm quickly going to cover what's happening underneath in each function call. So first of all, the initialization function checks first of all for all environmental variables that are required to get measurements out of the system, which are more specifically the Liquid ROCm events environmental variable, the ROCm GPUs variable, and the ROCm file path. And the first one is a definition of the events that need to be measured. The second one is comma-separated list of GPUs that are under observation. And I've said previously that we're going to focus on one GPU, but I'll explain later on how it get insights from the second GPU as well. And the Liquid ROCm file path, which is the output file path. And the initialization function, of course, initializes several data structures that are required by a Liquid. Okay, then the register function has two main purposes. First of all, it maps the region to the corresponding GPU. So for example, if you want to measure a specific sets of events on one GPU, it's then basically mapping the specific region to the GPU and thus to the corresponding events. And it's then basically allocating, initializing the result data structures, which are then required by the start and stop functions later on. The start function starts the measurement of the corresponding region. It first of all initializes the respective counters, which in some cases requires a read of the current state of the counters in order to calculate the difference later on to get the delta of the corresponding region. And it copies temporarily several information out of the system that's required for this process. And the kernel is basically an unmodified kernel, and it's simply doing our computation on the GPU. And the stop function is basically there to first of all read all values. Secondly, where appropriate, create the difference between the starting and the ending value to really get the delta or the event difference that's been performed by the specific kernel. And it then saves the results into the internal data structures. The close function stops the markers as well, just in case if we've forgotten to stop a region. It then writes all values into our target file and frees the memory and cleans, of course, everything up. Okay, now that we've an application that is theoretically able to run an application with the marker API, we then of course have to compile. And due to time reasons, I will basically go pretty fast through this slides. So we have of course to link against the LIKWID library. Then one thing that I want to explain in a little bit more detail. So if we want to run an application with LIKWID overhead, so with the overhead provided by registering, initializing, measuring the stuff, and another version of the same application without the LIKWID overhead, so to say, we can define the LIKWID with ROCm variable and then have this if def structure, so that we don't have to modify our application every time we want to run an application with or without markers. So that's why I've put this environment variable or this definition of this variable in place. And then we have more libraries to link against. And now that we've compiled our application, we of course want to run our application to get the insights. And at the top of the slide, you can see several export statements. And these are required basically to get the things in our paths and yeah, basically get the system up and running. And then the second part is more related to our application. So first of all, we can define our groups that are interesting for us. In my specific case, power average, as well as the memory usage and the ALU instructions that I'm going to focus on. Then we have in the second line the LIKWID ROCm GPUs variable. In this case, I wanted to execute my application, or I wanted to measure my application that's being executed on GPU with GPU ID 0.
Carla,
and then
we have 1 minute.
I'm already finished. And then we have basically our ROCm events, which define over there, and we have the ROCm file path. All right, now that we've defined everything, we're getting an output file. So the first one is basically number of observed GPUs, number of observed region, and number of observed GPU groups from left to right. Then we have the definition of our regions, and we have basically the result for each region from left to right. And don't worry, you don't have to evaluate the results by yourself, but you can also use the LIKWID native tools, which are then printing over time the results. And now that you've get the results, you can then take a look at the numbers and evaluate them. So here you can see the power consumption, the consumed memory, as well as the issued waves and the ALU instructions. And talking about roadmap outlook, so we're currently working on getting things to the main repository. And yeah, LIKWID has been extended by NVIDIA and more important AMD GPUs, performance, and the respective energy backend. And in order to get LIKWID with AMD GPUs, clone, configure, install, and then using LIKWID marker APIs, modifying the source code, compile, run, and then evaluate the results. Thank you very much. And heading over to you.
Well, if any questions, please send to the chat. Okay, and Carla will respond. Thank you very much. Okay, so John. Okay, John.
Okay. Share my slides.
Okay. Okay. We can hear you and we can see your slides. Thank you. Please go ahead, John.
Okay. So I'm John Malakami, professor at Rice University in the computer science department, and I'll tell you about the work that we've been doing to prepare HPCToolkit for Frontier. So HPCToolkit is a performance tool that is designed to measure, attribute, analyze, and understand performance of applications, libraries, tools, and the whole system software stack. And as part of the ECP project, we've been developing new strategies and mechanisms to measure and analyze performance on GPU accelerated compute nodes. And so the project, the HPC tool project itself is led by myself and a team at Rice University. And we work very closely with Bart Miller and his group at the University of Wisconsin. They work on the DynInst binary analysis toolkit, which is an integral part of what we use for HPCToolkit. So for those of you who are not familiar with HPCToolkit, let me just briefly describe its workflow. So when you're working on GPU accelerated compute nodes, you have a set of files and probably a makefile or something that builds them. And so you just compile and link your application the way you normally do, and you get your optimized binary. And then you launch your application using HPC run. And you can give this a set of arguments saying that you want to profile things on the CPU, on the GPU. On the CPU, we're using sampling, and I'll say a little bit more about the GPU measurement in just a minute. So we profile the execution on both the CPUs and GPUs, and we gather profiles, and we can also gather traces on the CPU and GPU. And then as the application runs, it reveals GPU binaries, and we record the GPU binaries for subsequent binary analysis. And so we run and measure our applications with HPC run. We use HPC struct to analyze application binaries and recover information about the mapping between machine instructions on CPU and GPU binaries and their source code. And so that produces program structure information. So we combine our profiles and traces with program structure information using a tool called HPCProf is a sequential tool, or HPCProf MPI is a scalable version of this for analyzing lots of performance data. And then this produces a performance database. And then we have HPC Viewer is an interactive interface for exploring the performance information. So for GPU accelerated platforms, we're measuring in several different ways. So on the CPUs, we're using the CPU hardware performance monitoring unit and also Linux timers. On the GPUs, we're using GPU hardware counters, and PC sampling is supported on NVIDIA GPUs. On the software side, we're using glibc's LD audit for tracking dynamic loading of shared libraries and the binding of symbols. We're using Linux perf events for measuring the application and also activity inside the Linux kernel if the permissions are such that we're allowed to measure that on systems. We're using a collection of GPU monitoring libraries, including ROC Profiler and ROC Tracer for gathering traces of GPU operations such as memory copies and kernel launches. And then for ROC Profiler, we're using to measure hardware counters so that we can associate hardware counter measurements with kernel launches. And then in general, in our software stack, we also use instrumentation for fine-grained performance measurement, but not yet on AMD GPUs. We do this on NVIDIA and Intel GPUs. So there's multiple measurement modalities and interfaces. So on the CPU, we're primarily using sampling. On the GPUs, we're using callbacks when operations are launched and sometimes when they're completed. And we're also monitoring a GPU event stream to monitor GPU operations such as kernel launches and memory copies. And then on NVIDIA GPUs, we're monitoring PC samples as well. So on AMD GPUs, we can collect profiles of GPU kernels that are written in HIP. So we can see kernel execution and memory copies and memset, and attribute these to the calling context in which they're initiated. And so this shows the profile view in the lower left. And so what we have here is a call path, and we have some metrics attributing GPU kernel execution, and then that gets attributed back to the source code where it was launched. We can also collect these profiles across multiple processes, multiple MPI ranks across multiple nodes. And so on the right, we have a trace view. And so we have timelines. And so there's a timeline flows left to right on the CPU. And then there's also GPU streams here as well. At present, the user interface isn't very good about telling you what the GPU streams are. They just kind of look like threads at the moment, but you can see from the identities of the operations, you can see that these are in fact GPU operations. So the next version of the user interface is going to address that, that restriction. So we have time flowing from left to right, and then from top to bottom, we have both CPU and GPU streams. So to give you an idea what this tracing is useful for, so this is a trace of WarpX, which is one of the ECP codes. And so this was running on 16 MPI ranks using 16 GPUs. And so what we have is there's one timeline for a main MPI thread. There's a timeline for an MPI helper thread, and then a couple of timelines for GPU streams. And so then we have this across 16 ranks. And the GPU activity is basically shown by these little flecks of color. And if you look closely, you'll notice that there's GPU load imbalance is evident here, because there's significantly less of these little flecks down the bottom. And so in fact, the top set of MPI ranks are using the GPU more heavily than the bottom set are. And so this is the sort of high level information that you can get from these profile views, similar to what Bill was describing with Vampir. So one of the things that we've been doing over the last year is working closely with AMD, Dhruva Chakrabarty, on the support for the OMPT tools interface for the GPUs. And so at Rice, we've submitted some new patches to LLVM OpenMP to improve the OMPT support for monitoring OpenMP on the host. And then we've worked closely with Dhruva on support for monitoring OpenMP offloading on AMD GPUs as part of LLVM's libOMP target and AMD's GPU plugin. And so the OMPT support, we now have host side support for the OpenMP tools callback interfaces that show you when GPU operations are being offloaded with OpenMP. And there's now support for tracing the OpenMP offloading on AMD GPUs. This gets generated as HSA operations, and so it's not visible with the interface that traces HIP with ROC tracer. And so there's now a new tracing interface, an OMPT tracing interface, where we can see the GPU activity. And so the status of this is it's currently available in ROCm 5.1, and Dhruva has submitted it upstream and is working to resolve some issues. And so we hope to see this in LLVM upstream very soon. So with the OMPT support that I mentioned, what this is showing is using OpenMP offloading with the mini QMC. This comes from the QMC pack project. And so mini QMC is just a small benchmark that embodies some of the calculations that are part of QMC pack. And so we compiled this with AMD Clang++ in ROCm 5.1. And what we're able to see in the profile view is we see this call stack that goes down to OMP target copy out. And we can map the cost. So it says actually that 69% of 70% of the GPU costs are associated with copy operations, and that those all map back to this Pragma OpenMP target offload, which is updating data. And so this kind of thing is being able to understand where your costs are being incurred and map it back to the source code is really critical for doing development in OpenMP. So this profile was collected on 96 threads and offloading onto the GPU using OpenMP on a local system we have at Rice that's using MI50 GPUs, but it works on the MI250X as well. So this is showing the same execution in the trace view. And what we have is there's a set of 96 CPU threads that are offloading. And in fact, what they do is they try to offload something, and then the threads end up stalling, waiting for the computation. These are synchronous operations that are being offloaded. And so what you see is that the CPU threads are largely idle. And then there's another CPU thread that is actually monitoring the GPU activity. This is part of the AMD software stack. And then the last trace line, which you can hardly see here, in fact, is actually showing all the GPU activity. And so what we can see then is we get actually for where the cursor is on the GPU trace line, we can see the full calling context of the GPU operation that's being offloaded. And so it tells us that there's a kernel that's being offloaded in the following calling context. Now here, it just says that there's a kernel that's being offloaded, whereas over here, we can see that it's actually being offloaded at line 179. And so that's something that we're going to add with the attribution to the source lines is something that we're going to add in this call stack view, because it's particularly important with these OpenMP directives. So with the University of Wisconsin, we've been preparing for fine-grained attribution of GPU performance. And so this isn't a capability that is yet available on AMD GPUs, but we're looking forward to having some support for instructional level attribution of performance information. And so in order to prepare for this, we're parsing AMD GPU binaries using the DynInst binary analysis tools for AMD GPUs, including the MI250X. And so DynInst recovers application control flow and identifies loops and their nesting. And we're working on developing support for GPU instruction slicing so that we can attribute costs for load latency back to the load instructions from the wait instructions where the load's complete. So HPCToolkit uses DynInst to analyze the AMD GPU binaries, and so we can analyze source lines, loops, inline call chains, and procedures. And so this is all in preparation for things to come in the future. So a couple of things I wanted to say a little bit about that we've been working hard on over the last year is we've been really trying to work on our tools to make them scale to be suitable for use on these exascale applications. And so one of the things we've been working on is this binary analyzer for CPU and GPU binaries. And so what we can do now is invoke our binary analyzer on a measurement directory for an application. And the measurement directory contains all of the measurement data, and it also knows what CPU and GPU binaries were involved. And so when you run HPC struct on a measurement directory, it'll analyze all of the binaries that are referenced within. And it does this by default in parallel. And so even for small binaries, we're using a couple of threads. For large binaries, we're typically using 16 or so threads. And we've worked very hard to make this highly parallel. And so as an example, I'll show you that we analyzed the 7.7 gigabyte binary for TensorFlow. So this is a CPU binary, which has 170 megabytes of text and machine instructions. And so this is showing using HPCToolkit's trace viewer, which is like Vampir's trace viewer in some respects. And what it's showing is that that there's analyzing the dwarf information for the 7.7 gigabyte binary highly in parallel. There's a somewhat serial piece of a serial code section here. This is analyzing the instructions in parallel, and this is assembling the program structure representation that maps the machine code back to the source code. And it does it all in 77 seconds for a 7.7 gigabyte binary on 32 threads. And so when you have ECP applications that involve like lots of CPU and GPU binaries, it's important that the analysis be relatively quick. So another thing that we've been working hard on is the post-processing of our performance data. And so we've been building a new version of HPC Prof MPI. And so what we're doing is we're analyzing profiles and traces using a technique that we call streaming aggregation. And so you'll invoke HPC prof MPI on a measurement directory on however many nodes you want. And the idea is that you would run one MPI rank per node, and then we'll run lots of threads across the node. And so the novel thing is that we now have a very highly, it's both distributed memory parallel, it's using MPI across nodes, and it's using a lot of threading within nodes. And so what we're doing is we're taking a set of profiles and we're aggregating the information into a concurrent data structure in shared memory, and then we're communicating across the MPI ranks to complete the aggregation across the nodes, and then this produces the profile data. And so previously, HPCToolkit was just using MPI-based parallelism, and the addition here is that we're using highly multi-threaded parallelism as well. And so to show you what the benefits of this are, one thing that we've done is some experiments at larger scale. And so we did some experiments on Perlmutter where we were running 2K MPI ranks with 2K GPUs, and we collected 32 gigabytes of performance data. And then we analyzed it on 16 nodes using 1,008 threads in 53 seconds. And so in addition to using this highly multi-threaded analysis, the other thing that's important is that we are switching from a dense representation of metrics to a sparse representation of metrics. And so what this shows is that for the original HPCToolkit, there was 2.7 terabytes of data because we were trying to compute GPU metrics for all of the CPU contexts, and they were all of the metrics were 0. And so this wasn't very useful. Now we have a sparse representation of metrics, and so the result of the analysis are about the same size as the measurement data. So we're keeping all of the measurement data that we record across all of the CPUs and GPUs and analyzing it quickly and with small output. So the other thing is that we're using a lot less resources than the application uses. So I mentioned that we're running it on 2,000 MPI ranks, and we're just analyzing the performance data on like 1 to 8 nodes. So this is showing that using 8 nodes, we can analyze the data in a minute. Using 16 nodes, it doesn't get much faster. It's 53 seconds. And then another thing that was important with the streaming aggregation approach using many threads is that we lowered the memory footprint. In fact, now we can use all of the cores on a node with HPCToolkit when we're analyzing performance data. Previously, we had to use either 4 or 16 MPI ranks per node because we ran out of memory. And so with the highly multi-threaded version, it has a much smaller memory footprint, and so we can use all the cores without blowing out of memory. And so what this is showing is using HPC Viewer to show our the parallel profile of analyzing the data for this experiment with 2,000 CPU, 2,000 MPI ranks, and 2,000 GPUs. We are analyzing 38 gigabytes of data with 1,008 threads in 41 seconds. And so this central part is the streaming aggregation, and all of the flecks of color are just showing activity. And so the thing that you should come away with here is that this part is very highly parallel. There's the white here indicates serialization. And so there's some serialization up in the front due to an MPI reduction. And then there's a little bit of serialization in the back, but the core of the analysis is highly parallel. So there are a couple of concerns that we have about where we are and things that need to be done for our tool set to work as well as we'd like. So we have some open issues with ROCm, ROC Profiler, and ROC Tracer. It turns out that if you sample using real time on the CPU, you can cause ROCm to deadlock, although we can measure things by sampling with CPU time. We've observed that ROC Prof deadlocks while using ROC Tracer to monitor ECP Warp X or Castro. These are both AMRX based codes. And so HPCToolkit will deadlock, but we can also deadlock just using ROCprof with ROC Tracer. And so there's some work that needs to be done inside AMD software stack to find out what's going on here. And also when using ROC Profiler and ROC Tracer together, we found that we were getting the wrong timestamps for the first application kernel. And there's some indications that maybe there's a firmware issue that needs to be addressed. So another thing is that currently the timings for OMPT are a bit suspect. So a 96 thread execution that's running for 140 seconds is reporting 11,000 seconds worth of memory copies. In fact, what it looks like is this is almost 96 times 140 seconds. And so basically, instead of measuring the time on the GPU, it's mostly measuring the time where the copies are queued for the GPU. And so there needs to be a little bit more work down in the OMPT support in the AMD GPU plugin. Also, there was a talk earlier today about the roofline model on AMD GPUs. And the roofline model is being computed with a larger number of performance counters than are currently available. And so the current set of available hardware counters are inadequate for doing roofline analysis of GPU kernels. And it's difficult, if not impossible, to understand the root causes of some of the performance losses. And so this morning, what Timur said is that they're expecting to make a much larger set of performance counters available in the May timeframe. And so that should address some of the concerns here. And then finally, I mentioned that we've been preparing for support for fine-grained performance measurement, but currently there is no support in AMD's software stack for fine-grained measurement within kernels. And so what that means then is all we can do is say that kernels are slow, but we can't tell you exactly why yet. And so we're waiting for that to change. So one more thing that I wanted to mention is that one of the things that we need is a reliable foundation for interposing HPCToolkit between an application and the operating system. So we're intercepting when threads are created and when applications fork, and when either the runtime system calls things like mmap or set signal handlers. And so there are many ways where various pieces in the DOE software stack can get around tools that are just using LD preload to watch things. And so we've been using the glibc's LD audit for intercepting dynamic library loading and symbol binding. But in the course of this, we found that there are many problems with the existing version of LD audit. And we wrote a long document and identified probably close to 20 bugs. And we've been working with the team at Red Hat and their collaborators on new support to fix the LD audit problems in glibc. And so this support has largely is available in glibc 235 with the exception of just a few small bugs. And so in order for tools to be able to interpose themselves between the applications and the operating system, we really need this support. And so this has to be available on Frontier and El Capitan. And so we've been working with HPE to make sure that support for this is going to end up in SUSE and then ultimately in Cray OS. So very briefly, HPCToolkit is working with ROCm 5.1. And so we're measuring and attributing performance of HIP and OpenMP applications on AMD GPUs using ROC Tracer to record GPU binaries and profiles and traces, ROC Profiler to measure with hardware counters, and the OMPT device interface to record profiles and traces of OpenMP activity. And then in near term, we're going to be completing our integration of our scalable measurement and analysis with our distributed version of HPCToolkit. Currently, that's in a branch. We need to do some things to improve the support for OpenMP offloading, add support for using hardware counters to monitor kernels that are offloaded with OpenMP, and also the rendering of traces. I mentioned that there was a lot of overlap that there was 11,000 seconds of memory copies that were being reported in a single trace line that's only 140 seconds long. And so obviously that's not right. And so we're gonna have to render this as multiple trace lines, and that's something that we're gonna take on in our next release. We also need to improve support for multiple threads, multiple tool threads. There's a ROC tracer thread, a ROC profiler thread, there's LLVM, ONPT threads. And so we need to be taking performance information from multiple measurement threads. We're coordinating with AMD and LLVM on getting the new support for ONPT into LLVM. And also we need to do some work. Once the new support for LD audit is available, we need to overhaul HPCToolkit to use these new facilities so that we can better observe what's going on in the application. Okay, that's all I had, Timur.
Thank you very much, John. So if any questions, please post on the chat window. Okay, so please unshare all the stuff. And Michelle, can you hear me?
Yes.
Okay, good.
Arno will share his screen.
Okay, so this is coming from Arno?
Yeah.
Okay.
No, I can't share.
You cannot share. John, you need to unshare.
Yeah, well, I got to find the Zoom window that's got the.
Okay, so
I'll just drop out and come back in. Can't find the window.
okay, good. Thank you. Arno, go ahead.
Yes.
Okay, we can see.
Okay, I start.
Yep. Please go ahead, Michelle.
Yes, hi, my name is Michel Dagenet. I'm a professor at Polytechnique Montreal. And today we'll be telling you about TraceCompass and various tools for HPC. Next. First, I will introduce the different components, LTTNG, TraceCompass, and Theia, and how they connect to ROCm. And then I will let Arno and Johan tell you more about the details and make interesting demos. Next. LTTNG is a very low overhead system and user space tracing. It was really created for multi-core applications, distributed applications. It has a lot of functionalities like log rotation, multiple simultaneous sessions, and so on. It was truly optimized for performance, such that you don't modify the execution of the system that you're trying to analyze. It has a very efficient binary format, per core buffers, zero copy transfers. It's very careful about not using locks or anything like that, such that it will not change the behavior of the application. It's very robust. You can put trace points, for example, in signals or non-maskable interrupts. And there's a counterpart to LTTNG, which is really for operating system level tracing. The counterpart is the user space tracing library. Again, that has been highly optimized for performance. Everything is done in user space. The data is written to shared buffers, shared memory buffers, and then there's a separate daemon that takes care of offloading the buffers to either the network or to the disk. So we have a very high performance source of tracing data. Next. Then we combine the user space tracing, user space traces, the system level traces with ROCm, as we will see. And then we need to analyze all of that. So this is where TraceCompass comes in. It's really a system to take the events, convert them to states according to the kind of model we want to build for the traced system. And it can analyze traces from different formats all together. And it can handle very large traces as well. Next. It uses a number of very existing modules for that. So it's highly modular, like the Monaco editor, Chromium for rendering, language servers. So the code used in the compiler to generate the executables is the same code that is used for syntactic analysis for the IDE. And it can also connect to debuggers. It's really, Theia is like Visual Studio Code for the cloud, and it's compatible to a level such that most of the Visual Studio Code extensions are working in Theia. Next. So now TraceCompass was split into the analysis part and the user interface part, such that the analysis part can be connected to a Theia. So now within the Theia IDE, we can have all the trace analysis. And it also works to a certain point within Visual Studio Code as well, if you prefer to do that. So it can really have the whole environment where you have your debugger, code editor, and so on, and you have the trace analysis all in the same place. Next. The connection to ROCm. So we connected the rock tracer and rock profiler. To do that, we created a new output plugin interface that can create some CTF output to be read by TraceCompass. We also made with the same interface a JSON output plugin, such that you can still have the default output that was there before we added this interface. And all this is being integrated by AMD in the next version of ROCm. I believe it should be available. And then we added analysis in TraceCompass to be able to analyze those combined traces with operating system level traces, user space trace level traces, the rock tracer, rock profiler traces, and we've even added the ability to take Scorpy events. So because of that, you can use that to really be able to analyze big MPI applications, and you have a complete observability on both what's happening on the CPU and on the GPU. And also, as I mentioned, we connected the debugger part as well, so we can connect ROCgdb to the Theia IDE as well. Next. So now Arnaud will continue the presentation. Arnaud?
Yes, so this slide will be presented by Johan, actually.
Yes, hello. So my name is Johan Eitz, and I developed the plugin for to generate STF traces at runtime through the ROCprof command. Here is a benchmark, a small benchmark for the performances of the interface on the plugin. As Michel explained, the CTF format is a binary format, and as you can see, first for the same program, the traces are in average 2 times later when outputted in a STF than when outputted in a JSON. And we have also some results for the tracing time. You can see that in average, the tracing time is several times faster when using the STF plugin. And it comes from the fact that ROCprof first generate text traces and then convert those text traces to JSON or database format by default. And when you output a CTF format directly at runtime, you don't go through the post-processing and conversion step. So we get this kind of results when using a plugin. As explained, other kind of plugin can be developed to generate traces in other kind of format by following the specification of the interface to load the plugin that has been implemented. Now I will show you a demo of how to trace a program with ROCprof and the interface and the plugin. To do so, I will share my screen. Can you stop sharing yours, Arnaud?
Yes.
Please. Thank you. Do you see my screen?
Yes.
Okay, so here we will run the GPU burn program that is located in the heap examples directory. But to do so, we will trace it with the plugin. So first, I installed the interface on this machine, and as you can see, we have a new option when using ROCprof. It's the output plugin option. With this option, you will specify in which location is the plugin. And for the STF plugin, you have to specify the place where the data will be, where the trace will be located after the tracing session. So I will show you an example of a tracing session. So the ROCprof command is usable in the same way as before, but we just need to to specify the place of the plugin. Here it's in teaser directory, and then we use a teaser option. And then we can run our program. And then with other tools such as Bubble Trace or TraceCompass, you can then display the trace. As we will see now, we will display it with Bubble Trace. And here we have our CTF traces with all the events in the trace. So it's very easy to use a teaser plugin. You just need to install the interface and to use a teaser new option to get CTF traces and be able to open the traces in TraceCompass. Now I will let Arnaud continue the presentation.
Yes, thank you. So in the next slide, we'll see the advantages of TraceCompass for HPC. So one of the main advantages that TraceCompass has is the ability to show different source of traces at the same time that are synchronized. And we'll see that it's very interesting to see GPU traces, so with GPU calls or heap calls or OpenCL calls, beside system analysis traces, showing all the processes that are running on the system, also showing memory allocation or other source of data. Also, with the integration and the plugin, we are able to have the requests done by the application, so with the different interfaces, so mainly heap, and then also the activity traces from ROCtracer. So we have the compute kernel dispatches and memory transfers, as well as the performance metrics that we can enable. And with this information, we are able to compute the different dependency links. So the dependency between, for example, a heap launch kernel call and the kernel dispatch that has been done. And so that's very useful to understand the different latency in the program while running the program. So for example, if we have a big latency between a heap launch kernel call and its execution of the GPU, we'll be able to see that. Another type of dependency is the wait dependency. So for example, we are waiting for the other kernels to finish on a specific time, and by doing, for example, heap device synchronize, we're able to wait for all the kernels that have been scheduled before. And mainly, the backward dependency will be shown using arrows to that call. So if I show now the demo, so for example, I have a small video here showing a trace that is a stress test running approximately hundreds of millions of kernel calls, kernel dispatches. And so the trace was run for approximately 1 hour. And now we will use the histogram to move inside the trace to be more efficient. And so here we will zoom only on a section that is of interest. And the histogram will only show the number of events with respect to time. So here we see some spikes. It's just that there is some events at this time. And so then we will open the flame chart API analysis. And in this flame chart, we are able to see the top lane, which is mostly green, is the API calls. Then we have the different kernel dispatches. And 3 kernel dispatches are shown. So we have 3 boxes. Mainly, it's just the difference between the user point of view and the hardware point of view. So we have the queues, which is the hardware point of view, and we have a streams, which the user uses to schedule its kernel. Then if we zoom in, we will be able to see the different arrows there. So for example, we see that we have a heap device synchronous call, and we see that we wait for the previous kernel to finish. And then after that, we launch another kernel, and that amount of time is pretty insignificant. And most of the time is spent on the GPU. Also, what is interesting is the trace is 1 hour long, but it's pretty easy to move inside it because all the different the analysis has been pre-computed, and so that way we're able to not read the trace every time we jump at another point in time. And so we can already see it. So that's the state that has already been written to an intermediary format. So we're able to zoom in on another section. Now I think, Johan, you will show another demo.
Yes.
Right. Okay. I will stop
Share
sharing.
my screen. So for the next part of this presentation, I will show you an example of a tracing session where I will trace several remote nodes. Those nodes will compute the PAPI. Yes, I will do it. Oh, my browser is blocking it.
Okay. Okay, we can see. We cannot hear you, Jon.
Can you stop sharing? I will, while you fix the audio, I can maybe show the next slides. Thank you. So in this slide, we'll see that we have developed also a plugin that allows us to debug GPU computations directly in the Theia Cloud IDE. So as presented by Michel, mainly Theia is a framework from which you can build your own IDE by plugging extensions. And so by creating an extension, we're able to connect with the ROCgdb debugger, and we're able to use the specific features of it. So we can step through the code inside a GPU kernel dispatch. We're able to insert breakpoints, view the different threads and call stacks. And the different threads, for example, are the wavefronts that execute on the GPU. And it's also possible to see the different agent info, so the different GPUs and the different dispatch info. So it's pretty interesting to see all this information while debugging the program. Johan, are you available?
Do you hear me now?
Yes.
Okay. I will reshare my screen. And do you still hear me?
Yes.
Okay. So for the next part of the presentation, I will show you a demo of a tracing session. We have two remote nodes that will compute the PAPI value with AMD GPUs, and we will do the communications between the two nodes with MPI, and we will trace the MPI calls with Scorpy. It's the script I'm using to do it. And as you can see, we will also collect PAPI metrics with Scorpy. And to do it, we will get three traces. One trace in OTF2 that we will convert to STF to be able to read it in TraceCompass, and two ROCm traces that we will collect on each node and then aggregate. So with MPI, we instantiate one instance of ROCprof on each node, and then we aggregate the different traces. So I'm running the program here. So it's we get it's running, and we should have got the trace now in the teaser shared directory. We have it's here. We have three STF traces, two for ROCm and one for Scorpy. Now I will open those traces in TraceCompass. So I will import all the directory at once. And with the import feature of TraceCompass, you can import all the traces at once. And so if you have a system with a lot of nodes, it can be very quick to open all the traces at once. Then we will use the create experiment feature. It will allow us to have the different analyses of TraceCompass synchronized between the different traces. So when you open traces in TraceCompass, they appear in the trace menu here. And for each trace, you have a list of analysis in the view menu. But we will use the experiment feature because it will synchronize the different traces between themselves. Here we have our 3 traces, and then we have all the analyses that are available for all the traces. Here we have a call stack analysis for the trace from Scorpy with the MPI calls, and MPI communications that are represented with arrows for one-to-one, one-to-all, and the all-to-one communications. And we have also our call stack analysis for the ROCm traces. And as I will displace the timeline, you will see that the 2 views will synchronize between themselves. And if you zoom in one view, it will also zoom in the other view. And so the different analyses are synchronized. And for the Scorpy part, we have other analysis. We have an analysis to display the perceived flows when doing MPI blocking communications on a timeline chart such as that, and an XY chart. We have a view with the states of the different communicators. Here we only have one communicators, and for each communicator we have the state of the different ranks. And we also have a summary view that for each kind of a function will show the proportion of threads that are currently in this kind of function. And that's it for this demo, and I will let Arnaud continue the presentation.
Yes, thank you. So
Okay, you have a couple minutes to finish.
yes, to conclude, we have seen that TraceCompass has a very modular architecture that allows for different use cases. So it goes from getting a thin UI client on a browser, and also to get more full-featured TraceCompass that Johan showed. And also there is a scripted access, so you can script analysis so that you can pre-compute them before a user wants to watch them. So this is a pre-computation feature is very useful for large traces. Also, it's able to leverage modern UR technologies by decoupling the backend from the front-end side. And so the if you can implement your own trace viewer for the trace server backend. Is very flexible, and by using the trace server protocol, it's possible to implement any front-end. Also, we have seen that Theia and TraceCompass have really a good integration with ROCm libraries like ROC Profiler, ROC Tracer, and ROC GDB. And we have shown a demo of the different features that we have. So thank you very much for listening. And we'll answer the questions, and you can reach us if you have more questions as well. Thank you.
Thank you, Arnaud. So you may post questions on the chat or just send directly over email. Thank you very much. So we have a TotalView. So Bill?
Yes, yep, I am ready. Let me share my screen here.
Please go ahead. Okay, we can see your screen.
Awesome.
Thank you. Please go ahead, Bill.
All right, thanks, Timur. Hi, everyone. Good afternoon, and thank you for your time today. I'd like to take a few minutes and talk about TotalView parallel debugging, where we are with AMD GPU debugging, and just kind of highlight some of the features and how you can use them all together in conjunction to solve some tough problems. So let me step through on here. And I'm going to do a quick introduction to TotalView for anybody that might be new to it, and then we'll dive right into the features around the different parts of there, and then I'll just do a quick synopsis of how to combine the techniques together to really solve some tough problems out there. Okay, so just quick introduction of TotalView. TotalView is a parallel debugger built from the ground up from the beginning to debug multiple processes, multiple threads, and really just complex applications. Complex can mean scale, thousands of threads, thousands of processes. Can also just mean massive applications that are, scale of 4 gigabytes in size with debug information. You could also be mixing different technologies together, whether it's hybrid applications, you combine MPI, OpenMP, and GPUs together as well. Using different languages, we support C, C++, and Fortran, and also a mixed mode of Python debugging with those as well. And of course, we'll talk a bit about GPUs today. We have a number of different technologies that augment the core capabilities of the debugger. I'll mention reverse debugging today, memory debugging, and some other ways that you can use TotalView. We support Linux, various architectures, Unix architectures, and macOS as well. One of the things I like to have people walk away from when they look at a tool like TotalView, it is a great tool for finding bugs, but it's a great tool for just seeing how your code is running, getting that view inside. Your code might be working fine, but you need to build on it, refactor it, extend it. Maybe you're new to a project and you just need to learn it. And there's a lot of great capabilities for using a debugger on a day-to-day basis and not just when there's a problem that you need to solve. Okay, so let's start off, we'll start a little higher level here and talk a bit about hybrid debugging models on here. You could be combining where you're running code on a CPU, but maybe you have a cluster and you're using multiple nodes out there using MPI to launch jobs across them. On each of the cores on the CPUs, maybe you're running multiple threads using technologies like an OpenMP. Trying to get a view of what's going on can be really difficult, and having a tool like TotalView to efficiently acquire that type of session, allow you to aggregate the information down of where your program is, where problems are happening, and viewing your data across that type of complexity can be difficult. Mixing in that using GPUs as well just adds further to that complication. It's a lot of power with the applications on there, but being able to really understand what might be going wrong, either with the logic or data portions of your application can be tough. TotalView fully supports this in a unified model, all one session on there, and you'll be able to really get a nice view across of the different processes that are involved, the different threads within them, being able to step seamlessly from host CPU code over to GPU code as well. And we'll dive a bit more into the GPU parts of things. I have a number of different videos. I'm not going to be able to have time today to go into demos of these different features here, but if you go to totalview.io under our resources area, you'll see a whole section on video tutorials and everything, and you can see these in action and TotalView in action debugging these different scenarios. Okay, so let's take a look at one aspect of GPU debugging, that's using CUDA. So we've supported debugging NVIDIA GPUs in CUDA for well over 10 years now. We support up to almost the latest versions. We're going to be supporting Hopper with the new H100 soon, as I can get access to some of these GPUs, and also the latest CUDA SDKs out there. One of the things that's really powerful about debugging this scenario is that it is all of one debugging session. So when you load your code, TotalView will automatically determine that you've got GPU code there using CUDA, and you can set breakpoints in both the host side and the kernel side. How does it look? So you can use set breakpoints on either side easily. And then when the code launches over to the kernel, your breakpoints will be hit. You can investigate the variables and really get a good understanding of how the code is moving back and forth, how data is moving back and forth between them. Now, it can be complex in there in understanding what's going across a single GPU, multiple GPUs across your cluster. And we have a really nice advanced GPU status view that aggregates the information down based on a set of characteristics that you choose in the ordering on there. And you can even filter and change how this display is built. And this will give you nice aggregated traces down to where your code is, how it's dispersed across.
I just mentioned that, I said,
can we have folks go on mute if you're not on mute,
removing a
please?
carpet and putting in.
Samir, you're on. Samir, you're not muted.
I said, I didn't say anything about architectural changes at all, but she said, no, nothing is allowed.
I think the hosts can mute them. Can mute
Your
him.
name is actually put on.
Let me see if I can.
Perfect.
Oh, it's muted. Okay.
Yeah, because it
All
was not possible to mute him right from my screen.
Thank you. Okay, so let's continue on and talk about the AMD side of things. So we've been working on the AMD GPU support with ROCm interface and HIP for quite a bit now. A very nice collaborative relationship with AMD on here and getting their updates and building that functionality into TotalView. So with TotalView right now, and actually this, the current version of TotalView that is released, our latest is 2022.1. You can do AMD GPU debugging out there. You can attach to processes, detach from them, set breakpoints, step through your code, look at instruction disassembly, do single stepping, including our fast smart stepping capabilities on there. So performance is really nice. We have full stack unwinding, including inline function capabilities as well. And I have some other screenshots I'll go through that will highlight some of the GPU navigation controls that we have. And we have some variable display in there. A lot more is coming with the capabilities of AFR compilers as further releases are done this year. Compilation is as follows on the few lines there, just preparing the application to be built and run under a debugger. TotalView takes and aggregates all of the individual threads that are under the GPU into what we call a super thread, and we represent that right along with other threads that are in TotalView's interface. This is the same technique that we've done with CUDA, and we represent that thread with negative increments of the thread IDs. That'll allow you to focus on that. It'll get you down to a device. Now, of course, in a couple of slides here, we'll talk about how we navigate across the different threads and organizations of those that are on the device here. So let me step one more in here. So we have some navigation controls that are very similar to what we have offered with CUDA in the past. Some of the language that's used on here differs a little bit for the ROCm interfaces here, but the concepts are very much the same. And you can navigate across the AMD GPU in a logical fashion, going across the work groups and different aspects of that, and the work items. Or you can look at it in a very physical way as well and going across the waves and lanes. And this allows you to change that context, look at the different variables, look at the execution and the context within that thread that you have selected, that super thread. Throughout the interface, we do show that information so you can see the grid dimensions, where the logical focus is displayed for the thread you're on, and the physical as well. So we do those in various stack displays and just other status displays in the debugger, so you understand that concept of the focus context of where you are. Now, like I said, variables display, there's some, we can display registers and some basic aspects of variable display there, but some of the dwarf information is not all there yet for debuggers to digest information and give you all of the different variables in your code. And that's coming. We're working very closely with AMD as they release the iterations of the compiler so that we can digest all the information and properly show the variables in the execution of your program. So right now, like I said, we don't officially support debugging, but the capabilities are in TotalView. So you can activate this with just using the -ROCm command line argument on TotalView when you start a application that's been built for running AMD GPU code. It's very simple to do that on there. Official support will come out later this year, but we continue to add capabilities each release of TotalView. We release 4 times a year. Our next release in May will have the 5.1 support, which is there in the product now. We can provide you an early version of it if you are interested and you need 5.1 support, but our current release 22.1 does have the 4.5 and 5.0 support within it. So what's coming? So like I said, variables and keeping up on the AMD compilers and make sure we pull all that information in to give proper values for variables. Watch points on global memory will be incorporated as well. Full dwarfs extension support. Debugging multiple GPUs. We'll be doing a lot of testing on that. TotalView we've tested on the MI50s and MI100s, but we haven't tested on the MI200s yet. That will be something we're doing soon. As OpenMP matures, so we can support OpenMP across the GPUs, we'll be doing that. And then we'll be looking to extend some of the other advanced capabilities, such as that global GPU analysis screenshot that I showed for CUDA, and being able to hopefully incorporate the same type of capabilities for the AMD GPUs as well. And as the API matures for on the ROCm interface, being able to support multiple versions of that, so that depending on wherever the system is here at TotalView, will be able to be utilized there as well. Okay, so that's high level of hybrid debugging, CUDA, and AMD HIP ROCm support. Let's dive into some of the other technologies that are around TotalView debugging so that we can understand how you would utilize the debugger and then combine these really together to solve some tough problems. So I'm going to begin with remote debugging. Nowadays, this is important, but it's always been important for supercomputers. We're not sitting in a lab. We're typically working across campus, across the state, or even across the country or the world to be able to access these systems. So being able to remotely debug on them in an efficient manner is really important. One of the capabilities that TotalView has with it is the ability to run its user interface completely detached from the backend system of where you're debugging. This allows you to run, say, on your Mac or Linux front end, that you can then have full client support, but efficiently and securely debug over SSH connections to the debugger that's running back on a cluster. Now, this works in conjunction with some other technologies that we already have for fanning out and efficiently debugging at scale on the cluster as well. Again, I've got some nice videos up on our website so you can see this in action. I go much more depth of how to configure these connections, how easy it is to set this up and do this style of remote debugging. Now, a technique that we'll often combine with remote debugging is what's called reverse connections. And what this enables you to do is basically decouple the launching of your job from when you are going to connect that to your remote, to your debugging session. If you're using Slurm and you're submitting into a queue, you don't know when your job's going to be run. So you need to be able to efficiently send that in. When it does run, is connect that to the waiting debugger on the front end. And so I've got a screenshot here where TotalView will ask you, do you want to accept this incoming connection? And you can just say yes. And at that point there, you can start setting up in your breakpoints and launch your parallel, resume into your parallel job and start debugging it. So all that's needed is to put TV Connect in front of, say, a typical srun command to enable this style of reverse connection. So it's really easy to use. And so if you have a full multi-tier, you're sitting in your laptop, you've set a queue in to launch your job, and then that connects back to TotalView, you can now work very efficiently through that whole type of cluster debugging workflow. Some other technologies that we have in TotalView that are very powerful. So one is called reverse debugging. And reverse debugging allows you to record the execution of your program and literally step backwards through that code to figure out, how did I get to where I was? Maybe it's a crash. Maybe you just need to investigate your code and go back through into an algorithm to look at some data that may have been incorrectly computed. Instead of rerunning and setting breakpoints again and trying to get to the point of narrowing down to what's maybe wrong in your code, you can just do it all within one session on here. Reverse debugging makes it very simple to do all of this. One of the things I like best about it is that I can save this session out. It's like a super core file, and I can load that later, or I can share it with a colleague. And that allows me to really spend some time in a postmortem way to figure out maybe what went wrong in there, or engage somebody else on my team to help me figure it out as well. And this technology actually works really well with, in say, a test or continuous integration environment. We are partners with a company in the UK. They provide a standalone version of this technology called Live Recorder, and it allows you to run it outside of the debugger, generate that recording file that I just talked about, and then that is loaded inside of TotalView so that it can then be debugged. So it's extremely powerful workflow there that allows you to really solve some tough problems. Memory debugging is right part of inside of TotalView. You can turn it on and conduct leak detection, just analyze overall heap usage, detect buffer overruns, and a whole variety of other types of memory issues that might be plaguing your application. Our technology is low overhead. You don't have to pre-compile, instrument your application or anything. You just literally click a button, and you can then start to get this data out of your application on here. It works, of course, in a parallel fashion, just like TotalView is built all around parallel. So you can do leak detection across your cluster and across your parallel job, and look at individual ranks to determine how they're using their memory, and if you have any that are just going beyond what you would expect, and figure out what's going wrong. Mentioned Python debugging earlier. Python continues to grow in use within HPC. And one of the use cases that we see a lot out of our customers is that they are combining use of existing or maybe high performant algorithms that are written in C, C++, or even Fortran. And Python makes it very easy to call down to these existing routines. And debugging that type of scenario is hard. You've got a mixture of languages, you're passing data between the different language boundaries there. So again, being able to see this all in one session and debug it is really important. So TotalView allows you to debug directly right into a Python application. And as you call into the C or C++ and you set breakpoints down in that code, now you can look at a really nice, efficient combined call stack of the two languages, examine the data on both sides of those language barriers, look at what's being passed down, what's coming back, and debug this type of tough scenario. Memory debugging, reverse debugging, everything all works right along with this scenario as well. So you can do some complex debugging down in your C and C++ code as well. This works in a parallel fashion out into a cluster as well if you're using this in a parallel job. So one of the techniques that I find or one of the skills I find on developers is to debug their code is, how do I combine these different technologies that are in a debugger, such as TotalView, to effectively solve tough problems? And really it comes down to understanding what is in my tool, what is in TotalView, and how do I utilize these to solve some problems? So you might have scenarios where you maybe have a deadlock between a couple threads, and what you can use in cases like that is combine reverse debugging and watch points. So when you get to that deadlock scenario, you can watch the data structures for such as a mutex when you acquired a lock. And when that mutex, various parts of that structure identify who owns that lock, when those change is when locks were acquired. And you can run backwards by watching that segment of memory, and when it halts, you've got the point at where the lock was acquired, and that's the point of where a deadlock could happen on there. So now you're combining multiple techniques together on there to solve a tough problem. As a parallel job runs, sometimes it's not always clear what's going on. It may be taking longer than you think. So use the ability to attach and detach from that parallel job. Basically go in, take a look, halt, look at the ranks, look at the call stacks, maybe step through some of them on there, and then resume it, and then detach from the job and come back again. So it's just a technique and some of the capabilities that are in the debugger that allow you to understand what's going on in your parallel job. There's when you're running in a cluster and you've got thousands of threads and lots of processes and going across GPUs, you don't want to wade through rows and rows of information. What you want to be able to do is aggregate that information down and basically pick that needle out of a haystack on there. So TotalView's process threads view allows you to choose a set of attributes and order them the way that you want, and we aggregate that information down. So a very quick display of that, those details there. You can figure out which ranks are maybe at a breakpoint and which one has not hit that breakpoint. And that can help you detect logic problems in your code of where something is not following what you expect it to do. Maybe one rank has crashed and all the others are running, so that will surface out very quickly on there. Multiple views of these attributes can be saved off and allow you to quickly toggle maybe between a thread-oriented view and a process-oriented view. When using reverse debugging, there is an overhead on that, but there's a couple techniques that you can employ to make it efficient when working with either a large application or a parallel job. One is really just turn it on when you need it. So get past initial data initialization and other type of setup work that the application's doing, hit a breakpoint, and then turn it on. And then you can record closer to where maybe a fault is going wrong in your application. So that makes it much faster to get to that point of failure. The other is that you can adjust, if you have limited resources on your nodes, you can adjust the size of how much information is recorded in a circular buffer that is utilized there as well. As you're debugging your application, you may find where things have gone wrong, but it may take a while to get to that point, or maybe it takes a while to compile your application. So utilize something like evaluation points to just quickly hot fix your code, do a hot patch right on the fly there. You can write a bit of code at that segment, correcting the logic there, use a go-to statement to jump over the code that's wrong and test it out. Make sure that it's working correctly on there. This can save a lot of time and testing something out before you have to go through and get to that point again on there. So I've covered a lot in a short period of time on here. As I mentioned, TotalView does have a lot of resources that I encourage you to go check out. So our main website is totalview.io. But the one you're probably more interested in is help.totalview.io. Here we have our user guides, reference guides, and so forth. Our blog is also available. Me, my sales engineers, and others, we're constantly adding just interesting articles and so forth about debugging, how to use TotalView efficiently, and so forth. In the video tutorials I mentioned, just short, nice 5 to 7 minute segments highlighting the different technologies and debugging techniques with TotalView. And it just makes it really easy to just learn a feature and start to utilize it yourself for your debugging needs. Okay, so like I said, I'm happy to answer questions in the chat afterwards, and you can always reach me at bburns@perforce.com if you have any other questions or just want to reach out. Again, thank you for your time today, and I really appreciate it.
Thanks a lot, Bill. Okay, so any questions, please send to the chat and to email to the speaker. Okay, Samir, Kevin.
Yes, I'll share my screen.
Okay, I can see it. We can hear you.
Great.
Good. You just may start. Please go ahead. Full screen.
So thank you for inviting me. I'll describe the features of Tau Performance System as they are relevant to our AMD software stack. And the key motivation for this work is that with growing hardware complexity, it's getting harder and harder to accurately measure and optimize the performance of our HPC and AI ML workloads. And the Tau Performance System aims to deliver a scalable, portable performance evaluation toolkit for these workloads. It provides a comprehensive profiling and tracing infrastructure, a toolkit that works well on AMD platforms. It's an integrated performance toolkit which has support for instrumentation, measurement, analysis, and visualization. It supports both AMD CPUs and GPUs. And specifically, we are looking at the HIP compilers, OpenCL, ROCm with support for ROC profiler and ROC tracer interfaces, and the HIPCC compiler. HIPCC compiler, as you're aware, is based on LLVM technology, and I'll describe in detail how we can support that. Tau supports PAPI and LIKWID for hardware performance counter access. It supports event-based sampling, direct instrumentation modes. For instrumentation, we have support for generating performance data at the statement level, at the loop level, at the function and file level, and compiler-based instrumentation using HIPCC compilers on the host side. We have support for Paraprof, the 3D profile browser that ships with Tau, Perf Explorer for cross-experiment analysis. We have support for generating traces that can be visualized in perfetto.dev or the Chrome browser. And Tau can also generate OTF2 traces natively for use in the Vampir commercial trace visualizer that comes from TU Dresden and GWT GmbH. So in the update for the AMD, we now support ROCm 5.1.0 and support AMD GPUs with ROC profiler and ROC tracer interfaces. This was released in 231.1 beta 3 and will be available soon in a 2.31.1 release. We have Tau and E4S integration, and you can see this in the Singularity container released by E4S. There is support for compiler-based instrumentation with HIPCC. And it's not enough to just instrument everything in a particular file. Tau provides an LLVM plugin for HIPCC that allows you to do selective instrumentation. So you can describe an include list of functions or an exclude list, which says, please exclude these functions from instrumentation. And so you can use wildcard characters for describing either of those. You can typically set an environment variable called Tau compiler select file and point to the file that includes these include or exclude list in the Tau format. We have support for CPU side for OpenMP tools interface in OMPT version 5.0, and we are working on, and it will be present in a future release of Tau, for support for the OpenMP GPU offloading features, which are there in the OMPT 5.1. We have support for HIPCC, ClangCC on Crusher with ProgEnv Cray, ProgEnv AMD. We have support for MVAPIC2 on Crusher, and we are working on integrating it in ECP applications and in outreach activities like this one. So on a platform readiness note, I should say that Tau provides hooks not just for the ROCm, ROC profiler and ROC tracer interfaces, but it has support for instrumentation for MPI, for COCOS using the COCOS profiling interface, for OpenACC, for OpenMP tools interface, and other runtimes for other GPUs as well. And often instrumentation is not necessary. You can just use the Tau exec tool. If you are doing instrumentation at the compiler level, we strongly discourage using instrumentation for every function because there can be too much overhead that is generated by approaches such as using the F instrument functions, because in a single header file, you may get thousands of constructors and destructors, and it may just add too much overhead if every entry exit for C++ codes is instrumented. We support the sampling with event-based sampling and hybrid measurement approach. And with this Clang plugin, now ready and shipping for HIPCC compilers, this makes it even more appealing to be able to cherry pick the functions that you really want to instrument and then have statement level samples collected by Tau. And we can also do call stack unwinding. So you can see where exactly that sample was collected and you can get aggregate performance data. And PDT or source instrumentation approach also still works with Fortran and C and can be used. The plugin for selective instrumentation works with Clang, Clang++, and HPCC compilers. And we hope to support Fortran in the future. Right now, it is integrated with the tau cc.sh and tau cxx.sh scripts, where you can they can read the tau compiler select file, and it's available as a standalone module tested with these compilers and with these ECP applications. Now, there are several metrics that you can collect with tau, hardware performance counter metrics, and if you're using PAPI, then you can look at the PAPI native avail tool to list the set of counters that are available to you. And then you can just use a prefix of PAPI_native while specifying one of these counters, in this case, the ROCm L2 cache hit for the device 0. And there are some limitations, of course, and there are some currently pending PRs that are being merged, and that will provide us with an even better set of counters, including hopefully soon counters that we could read in tau through the PAPI interfaces that give us details of the level 1 data cache and flop rates. And that capability is coming soon. It's already present in tools like MIPerf, and we hope to provide that in tau. We can get instructions, read writes, level 2 cache performance. You can have a look at this this website for the exact set of metrics, or the PAPI native avail is an excellent source for the full list of counters that are available. So tau and Apex is another measurement substrate provided with tau for asynchronous runtimes and other runtimes that are both available to use now at ORNL. We are currently investigating ROC profiler support in Apex. We are looking at some updates to PAPI and updates to tau and Apex when the software stack is updated. And we have been working with the AMD OpenMP Tools interface for instrumentation of OpenMP events, and are working currently on the offload event support in tau. Here is an example of tracing using the perfetto.dev, and tau and Apex can generate traces that can be fed to this perfetto.dev interface. And you can just load a trace file and see the detailed execution along a timeline display. And here are the GPU metrics that can be generated with Apex. This is how you can use tau's native OTF2 tracing capabilities to output an OTF2 trace file that can then be subsequently visualized using the Vampir trace visualizer from TU Dresden. You can just say tau exec with the serial, if it's not an MPI code, with the ROC tracer, and then provide the name of the application. And all the kernel executions, as you can see in this case for the GPU stream HIP, this is the add4 application from HIP. And you can see the triad, add, copy, and multiply kernels, and the copy from host to device and HIP free. All of those events are then available for us to visualize. So that's just the AMD GPU specific parts, but tau has support for instrumentation, measurement, and analysis for a large range of platforms and languages. Here is source instrumentation, MPI level instrumentation, and even instrumentation at the linker and executable level that tau provides to generate profiles and traces that can be visualized in Paraprof, Vampir, perfetto.dev, and other trace visualizers, including JumpShot, which ships with tau. So in case you're wondering what can tau be used for in the performance engineering of codes, well, it can show you where the application is spending its time at the routine level, outer loop level, even at the statement level, or the OpenMP loop level. It can show you the execution time in kernels operating on GPUs and how long it takes to transfer data. It can show you instructions executed in these codes, hardware performance counter data from PAPI or LIKWID. It can show you memory usage of the code, the memory footprint, the energy usage, the IO characteristics, even how the application scales. And to generate all this data, you need to add hooks to the code. This can be done at the preprocessor level using PDT, or the compiler-based instrumentation level, or you can even launch an uninstrumented application using Tau's TauExec tool, which preloads the Tau's dynamic shared object or shared library. And it generates profiles, which are aggregate summaries of performance data over all invocations of a code region, or traces, which can show you detailed timeline-based views, which show you what each thread of execution is doing at any point in time. And with profiling, you get the inclusive as well as exclusive measurements. There's a top-level timer in Tau called .tau application, which describes the total time on a thread of execution, whether it's a GPU thread or whether it's a P thread or the MPI rank. And here is the exclusive time. So I can see that these three loops are important and they take the most exclusive time. Tracing shows you the output with directed line segments that can show you message communication. And here is an example with jump shot, which shows you boxes within boxes to show you levels of nesting in the execution. And the perfecto.dev or Chrome browser, yes, this is the same Chrome browser that you probably have installed on your laptop, can show you the flame graph, which shows you the levels of nesting vertically. And you can see that the application calls this main, which calls this MPI, and there are communication patterns over here. And this is how you generate the data for both of these trace browsers. But what is interesting is that we have a tool called TauExec. It preloads a wrapper interposition library that can intercept the calls in a library and substitute one with another. We have support for other Tau options that can be enabled once this TauExec tool is used. So you can generate sampling-based data with event-based sampling, or communication matrix, or OTF2 traces, and MPI level, POSIX-IO level, OpenMP level data can be generated. But if there is one takeaway from this whole talk, it is that you do not need to modify the source code or the build system or even the executable in any way. You can just launch the unmodified binary using the TauExec tool and enable the different options. And once the data is generated, you can load it in paraprof, which looks like this, which shows you all the MPI ranks and threads of execution. And then these are the code regions summed over all invocations and the summary of that. And so you can stack the bars separately and see by hovering over any region what that function looks like over all the threads of execution. You can see the thread statistics table. Here is a thread statistics table where you can sort by the inclusive time. You can open up the keys over here and see the timing at the statement level. And you can see over here that there is a line number 228 in this particular solve subs.f file, where you can see the source code and see how much time was taken over there. And even you can look at the context events in a code and see how a particular system call can be further divided by the samples and see exactly where a sample is taken by using call stack unwinding in Tau. And here is an example of using Python with Tau with event-based sampling enabled. You just say Tau Python instead of TauExec, and then the same set of options apply. And here is an example of TensorFlow. and call site profiling that can partition the time in a call like MPI receive on the basis of different call sites, where you can see the function, you can see the line number, the file name, and where that MPI receive call took place, and see the context events where they can see a full executing context based on where the call was initiated, and the IO patterns like the bandwidth per file and bytes written to each file. So volume of data as well as read and write bandwidth are computed along a particular calling path that can include calls from Python. And this is the Tau 3D profile browser that can show you along one axis the MPI ranks, another axis you can see the functions, and then you can see the exact time taken in a specific line of code over here with respect to the threads of execution and the exclusive time. And you can change these metrics over here and move the function and thread slider. Where these two intersect, you can see the time in the height value and color value based on the selected metrics. And even see a 3D communication window where you can see the sender and receiver. To generate this kind of data, you need to set the TauCom matrix environment variable to 1 and then run the application to generate detailed statistics of point-to-point communication. Here is an example of using event-based sampling on the CPU side, where you can see the name of the file, the function name, the line number, and see exactly the time spent in the application by just saying tau exec-ebs or uninstrumented code, and see traces generated with tau with the Chrome browser and Vampir. And tau supports the Cocos profiling interface, so you can see the exact names of the kernels that are encoded in the first argument of a Cocos parallel for or parallel reduce operation. And you can see the breakdown. So tau supports many different runtimes, including MPI, pthread, OpenMP, OpenACC, and OpenCL, and ROCm, and Cocos, and Python. And the best part is you can mix and match these instrumentation interfaces. So you could say, my application requires MPI level performance data using PMPI, and it needs the ROC profiler interfaces. So you can mix these two together or use Cocos for that matter. And you can specify a given tag or a configuration of tau like this, where you can say, run this on 256 MPI ranks. If this is the uninstrumented execution, then with ROCm enabled with ROC profiler interfaces, you say -t ROC profiler and say -ROCm, or -t ROC tracer with the -ROCm. You can say -OpenCL, OpenACC, even IO profiling or OpenMP tools interface, OMPT, or event-based sampling using hardware performance counters, and you can specify file, function, or line level resolution. These are some environment variables. In particular, you may want to look at tau metrics. It allows you to specify metrics such as time and PAPI counters while you are running the code. You can turn on tracing, call path profiling, memory footprint computation, many different options. Here are a list of some of the options of the runtime environment variables. And you can see over here, you can install tau on your laptops using these instructions. We recommend that you download the Java as well, so that you can get the 3D graphics to work well on your systems. Here is a link for the M1 Max. And tau is available through the SPAC package manager. And you can use SPAC like this. You can just clone the SPAC repo, source the environment variable, and then just say SPAC install tau. Or if you select the SPAC compiler find and external find to set up the externals and the compilers, you can specify a given version of tau, and you can specify the compiler with the percentage symbol with the GCC 930 in this case, and say plus ROCm. So the Tau recipe for SPAC understands ROCm build options and other MPI options like this, where you can install Tau easily using the SPAC package manager. And it's a very versatile package manager. It has support for thousands of packages and is used in the Exascale computing project extensively in the E4S project. And E4S is a curated SPAC-based distribution which supports bare metal installation as well as binary build caches, as well as containers for a range of products. And it supports base images with GPU support as well as full-featured containers. You can create a custom image starting from a base image which supports the AMD GPUs, and you can validate the packages using the validation test suite. It's also available on AWS and GCP. Here is an example of a screenshot from an AWS image. We used this earlier today for the Tau and E4S tutorials. And I would like to thank our sponsors, the US Department of Energy, Department of Defense, National Science Foundation, NASA, CEA, and our industry partners, in particular AMD, for providing the support for Tau, and our partners at the Ohio State University, University of Oregon, ParaTools, University of Tennessee, Knoxville, TU Dresden in Germany, and Hewlett Supercomputing Center for their support. I would like to thank the Exascale Computing Project for their sponsorship of the Tau project. And I'll take any questions. Thank you.
Thank you very much, Samir. Okay, if any questions, we just can take them even verbally, right? We have some time left before the official end of the meeting. No questions? Okay, thank you very much. One more time. Okay,
and
so
please feel free to send me questions offline by email. Thank you.
Thank you very much. So this is like end of our session today. And thank you for attending. And I hope like next year we make even better session. It was like pretty good, and we have like pretty high attendance. It was varying from like 60 to 110 people. And so in average was like over 80 actually. So I would say it's pretty good. Thank you very much to everyone. Have a nice day. Have a nice evening.
Bye.
Bye.
Thanks, tomorrow. Bye. Thanks, you too. Bye.